systems, machine learning. First session is a title of Data Science, Big Data and Cloud Native Solutions with Fabian Gans and Milan Klöwer. So Milan is a climate scientist at the Massachusetts Institute of Technology. He did his PhD at the University of Oxford, working on climate model development, low precision in computing, data compression in information theory, predictability of weather and climate, and software engineering. During that time, he proposed the bitwise real information content as a way to distinguish between valuable information and noise in climate data, with the reference implementation bitinformation.jl. He currently develops speedyweather.jl, a global atmospheric model designed to be a computational research playground to develop prototype ideas on computationally efficient climate models. Then we'll have Fabian Gans, and Fabian is the first talking, so I take the opportunity. Fabian, but Fabian, do you have something to say about your background? Please feel free to.
Sorry, yes, I didn't send you my CV. Yes, I'm Fabian Gans. I'm working at the Max Planck Institute for Biogeochemistry in Jena, and okay, yeah, I think I'll stop because of the echo. So shall I try to speak again? Good, better. So I'm from the Max Planck Institute for Biogeochemistry in Jena, working on different Julia packages, also a large part of my work time, and among them DiskErase.jl, YaxErase.jl, yeah, EarthDataLab, NetCDF.jl, and yeah, a lot of things. Yeah, so thanks. So I guess Milan can start with the presentation. Yeah.
Fabian?
Yes.
Could you present yourself again, please?
Okay, I can present myself again. I'm Fabian Gans. I'm working at the Max Planck Institute for Biogeochemistry in Jena, in Germany. Have a background in physics, but already working for a long time in biogeochemistry and earth system science, a lot of climate model data, remote sensing data, and so on. And my main interest is in building efficient data pipelines, so for processing large-scale data. And and I'm using Julia since I think 2013 or so. And I'm author or maintainer of quite a few Julia packages like DiskErase.jl, NetCDF.jl, SAR.jl.
Fabian, I'm
Yes.
sorry, we are having some sound issues here. We'll have to try to arrange. Really? No funciona. Oh. Oh.
Hi, good morning, everyone. Does that work now? Yeah, perfect. Amazing. Yeah, thanks for the introduction. Sorry for the technical problems. Does that work with the screen sharing now? Perfect. Amazing. Great. Then I'll just take it off from here. So I'm Milan. I'm a climate scientist at MIT, as introduced just a few minutes ago. And today, what I really want to talk about are some of the data challenges that we face in earth sciences. Coming from climate data, my focus will obviously be more around weather and climate data, but most of the stuff will basically apply to anything that's some kind of gridded earth data. And as a motivation, I brought today this plot that is from ECNWF's data archive site. So ECNWF, that's the European Center for Medium Range Weather Forecast, probably the biggest data archive that we have in our field. So last year, they were just hitting the 600 petabyte barrier. They're getting very close to 1 exabyte now. And the question is really, in the coming decades, where would this data, the size of this data archive be? It's exponentially growing. So in 2040, it could well be hitting 1 zettabyte, by which it kind of would overtake Google's data archive from a couple of years ago, at least what we estimate its size is. And so you can really see on this graph of how important reasonable data compression is. So I've put in the figures here for a 10x or 100x compression, so making things 10 times or 100 times smaller. And so you can really see that this is an absolute game changer. Otherwise, we would easily end up with way too much data that we can basically ever analyze. And really trying to cut down on this data suddenly makes it much more manageable to store the data, but also to obviously facilitate the sharing, to send it around, to analyze it, and so on and so forth. One of the big problems, though, if we talk about data compression, especially in our field, is that we have such a variety of different types of data to look at. So these are just a few examples here. Left is brightness temperature as it's measured, for example, from a satellite, where you can see that if you have a really clear sky, there will be some really smooth data once the ocean is visible underneath, for example, but once there's clouds in between, it gets really, really patchy. If you look at things like other variables, you may even have absolute differences in their structure. For example, here nitrogen dioxide up in the stratosphere, where you can see like a pattern of the sun superimposed on some turbulence, but then nitrogen dioxide at the surface suddenly has a lot of point sources. You can even see ship tracks in it, and so on and so forth. So really finding a one-off solution for data compression here is a very, very, very tricky challenge. And so really as introduced already earlier, really the one thing that I want to talk about today is kind of this topic that I've been working on over the last few years, is the question that, because all our data sets basically just come in massive arrays of numbers, what do these numbers really contain? And which of these, well, essentially, because in the end they're zeros and ones, which of these bits do contain more information and which of them contain less information? So if you start here, just like looking at whatever array on the left, this is now presented obviously in decimal, or whether you present it in binary doesn't really make a difference, but you have somehow the most significant digits on the left, or bits on the left, and the less significant ones on the right. And so we definitely would agree that something like the sign is absolutely real, right? If I would just like swap the sign bit, we would immediately notice that something is off. But if I were to like swap one of the last bits in this data set, you probably wouldn't even notice that anything changed. And so the real question is there an objective way that we can separate out the real information that we have here on the left and the false information that starts at some point here on the right? And this really comes hand in hand with data compression, because the stuff on the left, as you can see, that there's a lot of similarity in the data, is very compressible, whereas on the right, everything is really noisy, so that's really incompressible. There's an entire information theory behind it that we've kind of worked through and formulated different metrics, and this is just the high-level summary of that. So this concept that we came up with is called the bitwise real information content. And the idea is really that you start with some grid data, you look at it in its binary representation. So for example, floating point numbers, and then you look at every bit position in a floating point number individually. So for example, you look at basically the spatial distribution of all the sign bits, or the spatial distribution of all the fifth exponent bits, and so on and so forth. And the question then is, if you were to look at one of the bits, what does this bit tell you about the neighboring bits? And so we really formulated this as the mutual information between adjacent grid points. And the idea is very simple, that you say, well, if somehow the neighboring bits have something in common, if they're basically certainly adjacent to each other, then there's more mutual information. And if they basically just appear randomly, then there's less information. And so that way you can basically squeeze this information about coherence of your bits in your data set. You can squeeze that into a single number for every bit position. And so we did this for a large data set. You can see here a lot of different chemical atmospheric variables on the left. You may spot variables like methane or CO2 in it, but there's also a lot of aerosols in it. And now we've color coded. So the darker the color, the higher the information in a given bit. And so this is just using the single precision bit encoding. So you have a sign bit. This is kind of a data set where basically all of the variables are positive anyway. That's why the sign bit does not contain any information here. Then you have a lot of information in the exponent bits. And then actually in the mantissa bits, a lot of information very quickly drops out. And so what we learned from this is that while we usually store a lot of bits, like if you store floating point numbers, like single position floating point numbers as it is, you will have 23 mantissa bits. Many of these mantissa bits actually do not contain any information. The next lesson we learned from this is that depending on the variable, depending on the field you look at, there will be different information. So some variables like CO2 require a much higher precision to store them at as some of the other variables. And so kind of like a one-off precision for all of them doesn't really work. If you then think about this as, well, if we kind of say, well, if there is some information towards the end of the bits that you could just cut off, it really lends itself immediately to a compression technique, right? Because once you store only the zeros and you remove them, the size of your files definitely gets much smaller. And here's an example where we've done this for water vapor. So on the very left of this field, it's basically the original data set as it is. And then towards the right, we've cut more and more of these mantissa bits off, and you can basically see then how the compression factor at the top starts to increase. So in the middle, we're around like 40 times smaller than it used to be. Whereas down the right, we really enter cartoon land. That's obviously we cut off much more information than we actually want to cut off. And so kind of like the sweet spot is somewhere in the middle. So really saying like, okay, well, if you start with a number, you replace the digits that you're not interested anymore because you've identified them as false information. You represent them with zeros, and the same holds for the bit encoding. Like it's kind of like the same perspective on there, where like you store your data in bits. Obviously, then you replace the bits with zeros. And so, in order to make this concept work in our favorite programming language, I've basically implemented the reference for this in this package called bitinformation.jl. But what I've found quite exciting is that there's actually also a lot of other people that have taken this up, mostly in Python-based data sets. And so basically, I hope that there kind of will be a community of people using this concept. In the end, basically all of these Python implementations just wrap around my Julia functions, because I find it's much easier to write many of these bitwise operations in Julia. And so just as the last slide here, I want to give you a little overview of how you can do this in practice. And there will be a hands-on session tomorrow where I will also be around, and I'm very happy to chat more about this. So the first step that you always want to do is you want to analyze your bit information content. So there's this package using bit information. Then let's say you take some kind of abstract array. I should have probably written this down here, but A is an abstract array here. You load it from a file, whatever you have. And really then the only function you have to call is bit information of that one. And that gives you a vector of as many bits as there are in your elements in your data set. So for example, for a single position, you will get a 32 element vector back. And every single number then just represents how much information between 0 and 1 there is in that bit. And so you can look at it, you can plot it as I've done here. So you see, for example, something like temperature has a different information than something like water vapor, and something that is completely random would have no information at all. And though in the end, it is actually surprisingly tricky to find the exact cutoff to automate that. But you can already see something like temperature, you may want to have like maybe 9 or 10 mantissa bits. But something like water vapor, you would probably need less. Once you know how many bits you want to keep, you can just apply this rounding function that is just binary bitwise rounding. And then you can see basically if you, for example, call the bit string function, you can see that there's a lot of zeros then towards the end, towards the lesser significant bits. And then really the last thing you have to do is just compress it. So depending obviously on what kind of data format you use, whether you use like netcdf or any kind of the other data format that are out there. Here, just an example using JLD2. So really just like if you then switch on the lossless compression that these formats provide, you'd basically just store that one and you will have a file that is much, much smaller than it originally was, while actually still containing all of the information that is necessary for your analysis. And this is where I would like to stop. And I think I'll hand over to Fabian Gans now, and I guess we'll take questions then towards the end. Thank you.
Yeah, thanks a lot, Milan. Maybe you can stop sharing your screen so that. Yes. Great. Okay, then as I said, thanks a lot, Milan, and I'll start now with the second part of the presentation, which is now less about compression, but about storing large data at all and analyzing large data. And I'll just begin with our study object at all. I mean, like, so the thing, I mean, when you talk about raster data, or I mean, like we are using it in climate science, you usually use these spatial temporal data, but there are also these data cubes of remote sensing data. You store them, you can often see them as multi-dimensional arrays. I mean, like, so this is what we usually store on disk. So it's basically, yeah, it maps very nice to a Julia array. It's a 3D array. And what your storage library usually does, I mean, like, no matter if you use, I don't know, a netcdf or HDF or whatever, is it lets you extract certain subparts of your data. I mean, like, so sometimes I want to read a single time series at a certain spot, or sometimes I want to extract like just one map from my data, or sometimes I need some rectangular hypercube. So but this is usually like the interface that is provided for me, and when you start dealing with these netcdf files also, or HDF files in the daily work, you get used to this. I mean, like, for you it's just data, but at least as long as the data is small. But if the data volumes grow and you have these kinds of data cubes now on very high resolution, I mean, like high spatial resolution and high temporal resolution, then you start running into problems with this kind of arbitrary data access very fast in the way that it can get very slow. So I mean, like, the problem is, okay, the data does not fit in. So imagine you have such a large data cube and it does not fit into your computer memory anymore. So you need to read the data on demand. And one of the main problems that when you look at this a cube, I mean, like, the way you want to store it is that your disk storage is not a 3D thing. Now we have an echo. Okay. Can you maybe mute again? I have an. Oh, okay, good. Like the storage on your disk is not 3D, but it's linear. So that means usually usually you have to I mean, like, data which might be close. sorry, there's one participant not muted, and I have this echo. Okay, I'll try again. Yeah, so that means data which is really close, maybe in time or in space, is not necessarily close on disk. So and another problem that you have when the data gets very large is that as soon as the data is compressed, it completely prevents random access of data which is on disk. So just imagine we give this whole data cube now into a compression library and compress it, and we just want to extract a single data point or a single time series from it. What you would have to do is that you would need to read the whole data set and uncompress it to do the random access into it. And to avoid or to partially avoid these problems that that you get is that you basically divide your big array, I mean like your big 3D data set into smaller chunks. And this is possible with like all the NetCDF and HDF libraries, but also with new file formats like ZAR, TiDB, HDF5 Cloud, or cloud optimized GeoTIFF. And because in these I mean, and these new formats popped up because like compression is really important, like in these cloud applications, and they also make it easier to store the data in buckets. I mean, like than it is for NetCDF. So basically there are different ways to chunk your array. I mean, like so you can chunk it only in space, for example. I mean, like then just imagine that you put these blocks into your compression libraries, and then each of these blocks of data, I mean, like here it's 1 year always, forms a unit in itself. And the big rule when accessing this compressed and chunked data is that the time that you need to extract some data is not proportional to the amount of data that you extract, but it's proportional to the number of chunks that you access. So that means when from this data set with this chunking, if I want to read a full time series, then I have to still uncompress all the data set. I mean, like so because because I can't just because I have to look into every chunk basically. If I want to extract a single map, that can be quite fast. I only have to extract a single chunk. So what you usually want to do to allow efficient access into all directions is that you basically do some chunking in time and in space. I mean, this is at least what I prefer because I'm doing a lot of time series analysis as well. And so when you access now, for example, a single map, then you only have to read a subset of the chunks. I mean, like still more data than you would need to read, but that's okay. And when you want to access a single time series, then you also need to read only a subset of the chunks. So, and this is really what this chunking is about. And what we now need, I mean, like this is now the data side, and what we really need is basically a library that can efficiently work with these chunked arrays. And since this is implemented in many different file formats, it would be good to not re-implement this for every file format, but to basically have one library that deals with it. And this is this diskarrays.jl package that already Raphael has mentioned on Monday. I don't know how much he talked about it in the hands-on. I couldn't attend this one, but it basically does two things. I mean, like it provides an abstract array implementation for arrays which have slow random access. Right? So yeah, I don't know if I should do this detour, but when you look at this abstract array interface, you see it's when you usually use it, then it's completely bound to efficient access to single elements. So all you usually define for an abstract array is how to read a single element for the array. And then the Julia base library will basically always, whenever you do more complicated indexing, it will just fall back to indexing into individual points. And as I explained, this is really not possible for these kinds of arrays, because if I do like here, if I want to read a full time series and I just start looping through the time steps and extract every single point, then I would have to, then I have a lot of additional reads and a lot of additional calls into the C library and a lot of uncompression. So this is just not practical. And so that's the first thing that it provides. I mean, like it basically captures all the gets index and show and so on, and makes sure that there's never a random access, never an access to single elements, but that always blocks of data are read. And the second thing that it does is that it provides primitives to handle these n-dimensional chunks. I mean, like, so to talk about the chunking structure of arrays. So these are basically the two main things that DiskArrays.jl provides. And it is already implemented as a backend for data access in ArchGDAL, in NetCDF.jl, in SAR.jl, and in grip datasets.jl. So these they all depend on disk arrays. And just as a short demonstration, so when you use, for example, the ZAR package, which opens its multidimensional arrays as a disk array. I mean, they are abstract disk arrays. So here I open a data set directly from the cloud. So this is like now stored in Google Cloud Store in a Google Cloud Storage bucket. That's just some CMIP6 run. I open the data set, I get a variable, and the first thing that disk arrays is doing is that, I mean, although this is an array, it doesn't print me the typical Julia array because it doesn't want to do any data traffic. It just shows you the size of the array and the type of the array, but it doesn't print you an overview of the data. I mean, like, so basically this is what you have. And I, through the disk arrays package, I can ask, okay, I can ask the array, okay, what are your chunks? I mean, like, this is this each chunk function, and then it gives me back an array that's tells me, okay, I have this chunking structure. So this array is not chunked in longitudes, not chunked in the latitude dimension, but only in the last one, only in a time. And there we have 116 chunks. And you see the indices of each of these chunks. So this is very useful because you can use this to do like batch processing of your data, and you know that you will always access your data set in a chunk efficient manner. And in the detail, it gets a bit complicated. So, for example, when you create views, I mean, here, let's do something. Let's just take every second longitude and every third time step, and until the time step 5000. And I still can look at the chunks, and you see that then the chunk sizes are adapted, but they still align with the original chunks of the data. And although I have now irregular chunks because I have these 3 steps and so on, I mean, like, all this is possible, and there's a lot of nitty-gritty detail work, especially with views and with strange views that we implemented in this disk arrays package, or that you extract like a number of time series like at certain points or so. I mean, like, that you give a long vector of longitudes and latitudes, and you just access the array at some longitudes and latitudes. I mean, like, this is you can still read from the data, but it's programmed in a way that it always makes sure that when you do some get index operation, that every chunk is accessed only once. So that this is still quite fast on your machine. Okay, and a typical workflow when you want to do some data analysis would be, as I mentioned, I mean, like, so you have your array, and then you just do for index in each chunk of PLS of my disk array, and then you basically get these indices always as ranges, as boxes, and you know, okay, in the next step you should do something with this chunk, and then you know that your access is always chunk aligned. And yeah, we also implemented basic reductions, like, for example, simple reductions over a dimension. So I can do, this is now again on the remote array, I mean, like, which needs like some internet connection to Google Cloud or so, and then I can do a mean over these steps over the third dimension, and it will read the necessary chunks and do the computation in a much more efficient way than if you would use the normal abstract array fallback. And also broadcasts are implemented, lazy broadcasts, as was already shown by Raphael on the first day. So, but then what should we do when we want to go a bit beyond broadcasting and reduction? And so what about typical like map slices operations, or when you want to do multivariate operations? So for example, you have like some disk array here, one array here and another one here, and I want to operate on them together. I want to do operations in parallel. I mean, like, that's the main point of moving data to the cloud and have chunked things so that different workers can work on different parts of the data. And here we made this package, this JuliaEO package, which is an attempt to solve some of these issues. And so it's first of all, when you look at it, the Yax arrays library, it's yet another library for arrays with dimension tables and values. I mean, there's already a zoo of them. But the special thing about this one is that behind the scenes, a Yax array is defaulting to out-of-core computation and to out-of-core storage from the start. That means this has in some ways the effect that it sometimes feels a bit more awkward to use, and it's much less documented than rasters.jl. So when you're a beginner working with data, and especially when you have a bit smaller data, I would also really suggest you, okay, use rasters.jl, but there is a lot of work invested in these large-scale processing problems and large-scale processing tools. And just to show a very short example, you can open this. You load the Yax arrays package. You open a tar data set, and then you see, okay, I have longitude, latitude, and time dimensions, and I have a lot of variables. I have some variables in there like air temperature, land surface temperature, GPP, like gross primary productivity, and so on. Some land surface things, and I can also merge the different variables into a new axis. I mean, like now I get a 4-dimensional array, for example, when I just call cube here, so that I have longitude, latitude, time, and variable as another dimension. And you see the total size of this array is now 33 gigabytes. This is all happening on my laptop. I mean, like so the storage size is smaller. I mean, like this is basically the uncompressed size that it's showing here. And yeah, I can, as I said, I mean, like, so one thing that we implement is a map slices. So for example, I can define my function, apply median, and then I just check for nones and compute the median of the data. And then I can just say, okay, map slices, this apply median function, I apply it on my data cube across the time dimension, and I give it like some maximum cache size, and yeah, then it's just computing it. And so here on these 33 gigabytes on my laptop, it takes 62 seconds. Okay, it says there was 69% recompilation. So yeah, I mean, like, it's actually quite fast, and it can't load all the data in memory at once. Yeah, so yeah, that's the result when you plot it. So you get then a map of the median, and basically now median has been applied to every time series because I specify the stims equals time here. And it's doing this computation. And so this all sounds quite natural and simple, but there's actually a lot going on in the background when you call this map slices over the dimension here. I mean, so the first thing to know is really that this Yax arrays is working together with disk arrays, and it's aware of the chunking of the underlying data. So it really looks deeper into your data set, and then it says, okay, I need to loop through this data. So it looks where to get full time series from. So what it will probably do is, okay, it decides on this first chunk, okay, I need to read these blocks of data to get full time series. So it will read this whole block that I highlighted here into memory. And then it will start, okay, to take the first full time series, and it will basically run this inner loop now through the single pixels and process the time series and compute medians on them. And then when it has arrived at the end, it will read the second set of chunks, will start again its inner loop to process these time series, and so on. And it will do this, like there is some optimization in the background to use quite large processing windows, but to do this always aligned with the chunking, with the chunks of the underlying data. And of course, this is very trivial to parallelize. So whenever you load some workers, you use the distributed JL package and you add some workers, it will automatically distribute the loading task of data across different workers. So basically then when you have two workers, they will both now load their piece of data and then start processing these beams of times. And also, when you have multiple threads on each worker, it will do this computation also on the multiple threads. So you don't need to care about this. I mean, just with the single map slices line of code, all this will be happening in the background. So there are also much more complex workflows possible, of course, then the interface gets a bit more complicated, but you will see that in the hands-on tomorrow. And but just to summarize, the general philosophy of this Yax-Arrays JL is that the user comes with some function they want to map over a big data cube that is chunked, and then you basically give it to Yax-Arrays, you tell it what to do with that function, and then Yax-Arrays maps it over the data on disk and writes the output. And yeah, so okay, I'm running a bit short of time. I just saw just the things that it does not yet provide the Yax-Arrays JL package. It's not doing lazy function application yet when you do this map slices. So basically, it's always executed at once, the operation, and there is no coupling yet to the rasters.jl and dimensional data.jl universe, although there are some conversion functions. I mean, like, because we know that many people like to use these packages, and we also like them because it has very intuitive subsettings and so on, subsets and so on. And one of the next steps will really also be to work towards this, that you basically don't have that we will try to put what we have in the out of core processing on top of the rasters.jl, but that's a little bit difficult, yeah, because things get intertwined and so on. So, but that's something we want to do in the future. And we also provide a table interface. I mean, like, so Raphael has already described the concept of how you can make a dimensional array or like a geo array to a table. I mean, we also provide this, but as I mentioned in the beginning, everything by default is out of core. So you can create such a table here. Now it's I use this cube table and I just put it in. I say, okay, GPP is this data cube and air temperature is this data cube. And it just tells me, okay, you get some data cube iterator with 40 subtables. Yeah. And the point about this is that that it already says, okay, I don't load any data, but I give you an iterator over tables, and I can just take now, for example, the 33rd subtable, I mean, just some random table, and convert it to a data frame, and then you will get a subset of the data which fits into your memory. I mean, so this also has an argument where you can set, okay, how much memory do you want to allocate to each of these subtables? So, and this is really a structure that you can nicely use for out of core aggregations of data whenever you need them. I mean, like, so you can, that we will have an example tomorrow in the hands-on where you can also do like a country mean of certain variables, but then with parallel processing, like in a using the distributed .jl package. I mean, so that you can really distribute your computations also that happen on this kind of table level. And so that's a short overview, and I hope Felix will explain this in a much better detail tomorrow in the hands-on session that he's going to give on this Yax-Arrays JL package. And I just want to say a few words about the future, like the future plans that we have. I mean, as I already mentioned, I mean, like, rasters.jl is doing many basic things, especially also the coupling to the whole geo interface world and rasterization, and but also the simple opening of data is doing many things better than Yax-Arrays is doing, like in the basic array handling. And I also have the feeling that it's for myself and our group impossible to maintain such a large set of functionality. I mean, like, so much on the processing side and on the data access side. So we will try to concentrate on this out of core processing part in the future. And I have recently started a new package called disk array engine.jl, which is really supposed to provide all this out of core processing, but on the disk array level. I mean, like, not on Yax-Arrays, but on the disk array level, so that it will be much easier to implement this functionality than also on top of a rasters.jl array. So that's basically what we want to do in the future to make this more accessible, all this machinery. until then, you are still very invited, to try YAX arrays, to try the package. Yeah, be aware that that's like most of the development, or at least my development of new functionalities, will happen in this disk array engine, which is not yet ready to use. But I started and putting in functionality and so on. And yeah, so and yeah, also this disk array engine, it will provide like interfaces to do some operations on large array, but it's probably not meant for direct user interaction, but just to be called by other packages like rasters.jl to do some computations in the background. So if you want to, you can keep track of what is happening there if you're interested. Okay, so yeah, thanks for your attention. And I think if you have questions either to myself or to Milan, feel free to ask them now.
Thank you. Sorry for these. Sorry for these technical issues. We'll now have a short coffee break. We'll be back at 10:15. For those who are online, yes, we'll be back at 10:15. Okay, thank you. sessions. The 1.1 will take place here, and it's entitled of Simulating Oceanic Pathways of Plastics, Pollutants, or Marine Ecosystems.
Hello everyone who's here. Hello everyone who's online. Welcome back. So I'm Gaël Forget, and I'm going to present this one now. A hands-on session on simulating oceanic pathways for marine litter, pollutants, and marine ecosystems. I have a few slides to start, and then I'm going to show you some notebooks. All right, so I'm going to tell you about methods in Julia that we have already developed to simulate pathways of various materials and quantities in the ocean. They're also applicable to the atmosphere, so maybe my title is a bit too narrow in a sense, but I'm going to focus on the ocean applications. And why this is relevant to a meeting on Earth observation? Well, partly because of what I was describing yesterday, and also because generally speaking, anything in the ocean or the atmosphere has to be viewed as, life within a fluid in movement. So you have to account for that that element, even if you're looking at satellite data, for example. There is underneath moving matter. Just here, I'm going to give you this little bit of background on ocean circulation and transport processes, briefly, because the audience is not necessarily accustomed to the topic. And then I will get into the notebooks. So here are some references if you want to know more about these problems. I have made a very opinionated selection amongst things that I'm involved with. There's a lot of science in climate and oceanography that has to do with transport processes from the global scale. So this first paper that I highlighted here is about ocean heat transport, and makes the case that the way that it's normally defined is rather sensitive to a reference temperature, and that we have a better way now to handle that, or something that's less sensitive to these arbitrary parameters. The second one is closer to what I'm going to show you today. It's about simulating the so-called Atlantic meridional overturning circulation, often also termed the conveyor belt, or looking at it from the perspective of pathways. And so this is work that Louise Rousselet and Paula Chessy did with me, where they did, Louise specifically, simulations of trajectories over thousands of years, using Fortran in this case. The third one is the closest to the topic today. This is work in collaboration with the colleagues at the Ocean Cleanup Project. Alexandre Pétavin was the lead author. And so he did a data simulation exercise showing that we can use concentration data for marine litter, plastics, debris and stuff into a dispersion model. And so finally, the last two are Julia packages that have been developed by myself and colleagues, specifically Zhen Wu for the second one. The individual displacements package is one that really is focused solely on simulating pathways. And that's what I'm going to illustrate today. Plankton individuals is a agent-based model that focuses a little more on the representation of marine life. So what does that look like in practice? This is from Louise Rousselet's work. I think it was a schematic that was in one of the papers. You're looking at this so-called conveyor belt structure. And you see this is a plot as a function of depth and latitude over the globe. So this is sort of the three-dimensional ocean circulation once you sort of collapse the longitude dimension. And so this is one of the key aspects of ocean circulation for climate. It's not exactly what I'm going to focus on, but I will draw your attention to the so-called subtropical cells in the upper ocean. These are the ones that we're going to be talking about. So we're going to be less concerned today with the deeper stuff, the longer time scales, and focus more on the near surface. Another view on this from above, this is now, if you're looking at the gray contours and the black contours, these are the so-called ocean gyres. So you see, for example, that in the Atlantic, you have this dark contour that corresponds to the Gulf Stream. And I'm going to tell you briefly what the colored contours are, but don't worry about them now. And so this is sort of the circulation in the ocean that comes from, say, the Gulf Stream bringing waters to the Azores, and then circling back through the Gulf of Mexico and so on. So there's a lot of these features in the ocean. A massive one that you see in the southern part of the domain is this so-called Antarctic circumpolar current. The colored contours, as a side note, is the divergent term. So this corresponds to the flux of heat typically from the tropics to the subtropics. Won't talk too much about this today, but there's one notebook that does that for you in Julia now. This decomposition essentially of ocean heat transport or ocean transport into these divergent and rotational components. If you kind of have a memory imprint of what you just looked at, this is another view of this sort of horizontal circulation. You're looking at 300-meter depth, where I have seeded in a flow field a bunch of particles that we then, thank you, that we then track as a function of time following the currents. So this is exactly what we're going to be doing in the notebook and the application in a minute. I wanted to drive your attention to the fact that this resembles the previous map because we are kind of a little bit below the surface. But when we go way up, things look quite different. And so that's the point I was trying to drive home. This is the sort of the view you would get from following the fluid in the near surface layers. And so these are the ones where the vast majority of marine life takes place. This is also where the plastics that is floating material will get stuck to a large degree. And so that's the one we're going to focus on, just following water that we are going to assume is floating near the surface along this circulation. And I've highlighted on the left here the fact that you see those trajectories sort of collapse or converge to a certain latitude. This has to do with ultimately the wind-driven circulation. And so that means that you have the flow field sort of converging and bringing all of these plastics to a particular point. So that's the origin ultimately of the great plastic patches, as they are often called. In this simulation that we will do, there will be even too much convergence for reasons that have to do with simplifications. But this is sort of the broad view of the problem. It's like we put plastic in the ocean, it's going to circulate around, and it's going to tend to converge in particular regions that happen to be a little south of where we are, around 20, 30 degrees of latitude. Right. I lost my water bottle somehow. So it's okay. So coming to Julia now. This is an excerpt from the documentation of the individual displacements package to give you the flavor of how you operate it. So it's a high-level API, which involves a little bit of Unicode to make things easily interpretable. Oh, great, thank you. So the way that this works out is we put together a data structure that contains the flow field specification. That's going to be the ocean circulation that the Lagrangian particles are going to be exposed to and following. Then we define the initial positions of these individuals or particles that might be a concentration of plastic, that could be also a patch of the marine ecosystem that each of the particles represents. And then we're going to call in number 3 this integrating functions over some time. So you see it's written a little bit like you would do in math on purpose. Once the simulation takes place and after it has taken place, we can then post-process the output from the differential equation solver that I'm going to use. And we can make more diagnostics, such as sampling from gridded variables, say temperature. We want to know how, for example, a patch of plankton is going through different temperature ranges that affects them in their survival and their growth. And so this is number 4, and step 4 is step 5 is basically go back to number 3 and keep number 2 and keep going. So we can do this over millennia or over very short time scales. And I'm going to show you now a few examples after I take a quick drink of water. Any questions thus far? All good? Okay. So this was the ocean transport primer. Let's put it this way. And now I'm going to go to the actual hands-on part. So I am here in our Docker environment, a container, as we call it. And I have already opened my notebooks. Now, one of the issues we are going to potentially have is with data inputs in one of the notebook. So I have provided them here to the people in the room on the USB drive. This file here called echo.tar. And this file called grid.tar. For the folks online, you should not have to worry about those because the notebooks are going to download them automatically for you. We are just here in a situation that's a little different because we have a lot of people in the room and we don't want everybody to download at the same time from the Wi-Fi, which would saturate. So with this said, I've already pre-opened all of the notebook to make this a little easier on us. And I'm going through a few different cases. Let me briefly show you this notebook that I will go back to later on in the afternoon. This is to depict again the ocean circulation estimate that we are going to use. These are what are called reanalysis products or model data synthesis. The ECHO project is one that is dear to my heart because I've been a long-term participant in this effort. It's led by NASA and these days by NASA JPL specifically. You will find here a lot of things that might look familiar from my presentations before in the week, and a lot of very useful information. So please follow us and consider using our products. You will find also, since I'm here, I'm going to show you a little web page that describes the kind of analysis tools that we have created. We have things to analyze our model output and our solutions in various languages, including this one that you've heard about this week called Julia. So we have this nice story map, as it is called, that you can explore later at your convenience, that will tell you a lot more about this project and how to use it in Julia and so on. I'm not going to spend too much more time on this, but ECO is this project. This is the notebook that lets you explore it interactively. You will find it on the Docker image, as well as on the Julia Climate Notebooks webpage, which I will remind you is here. So this is the web page that is found on the Julia Climate organization and /notebooks. Okay. It has a long list of notebooks in it. This is what also we are using for the Docker image that that will be maintained moving forward. The notebook in question is called ECO Standard Plots, and all I'm going to show you from this at this point is this view of the horizontal circulation from above, integrated top to bottom as before, and highlight to you that there is a lot more in this notebook for you to look at. So for example, this so-called conveyor belt or overturning circulation, here's one view of it. I've mentioned also ocean heat transport, so this is that. We have various transports across different regions. So this is, for example, this Antarctic circumpolar current. Probably somewhere have, let's see. There's the Davis Strait. You know, a lot of the different gates in the ocean that separate ocean basins, and so on and so forth. So this is one notebook that you can look at. We will maybe take another look this afternoon at this one. So this is the sort of timing, so-called Eulerian view of the problem, where you're just looking at map on the gridded plane. But what we want to do today is slightly different. And we are going to do 2 or 3 notebooks that have to do with this Lagrangian point of view, where we are going to, instead of just looking at a gridded field, we're going to put particles in it and we're going to follow them. So when you look at weather forecast on TV, you have similar views sometimes of the wind fields in this kind of dynamic motion. So that's what we're going to do. Maybe I should take a little break, ask if there is any questions or comments, concerns. Everybody's happy? Good. So we're going to start with sort of the simplest thing you can think of, but that's quite relevant, which is this random walk problem in a plane view. So this is something that a lot of people would use in their examples when they talk about this, because it's extremely simple to code. All that we do is we take a original point, and at every time step, we move that in a random direction by, I think, 1, in this case, just 1 value, but it's randomly going in one or the other direction. So by the end of the simulation, you're going to see a pathway like this, which has started at 0.0 somewhere here in the middle. And then let me try and rerun that to make sure it's live. Oh, there we go. And so that's what this notebook does. It's very lightweight, so that's a good start. Also, I'm going to mention the packages that it uses, which nope. Where did I put those? Huh. Well, there we go. That's the difficulty with hiding stuff from myself. So in this notebook, we're using three things. We're using, first of all, it's a Pluto notebook. We're using Pluto UI for the interactivity and reactivity part. Karomaki for the plotting, and then this climate models.jl package that I created and presented at JuliaEO a couple years ago. What climate models.jl is, it's a driver of ultimately models that are relevant to climate or oceanography or atmospheric science, models that can be of any nature, written in any language in principle, at least any language that we are able to use on a Linux machine. So it provides a few functionalities that I'm going to highlight. And it's presented in my JuliaEO talk last year. But before I do that, I'm going to tell you about the random walk process itself. So the random walk is we initialize a point at 0, 0. And then, like I said, we just write a loop that's going to randomly add +1 or -1 in the two directions. And that's it. So it's super simple. It's a loop that has a function of time steps here, ns, in this case. And we can change ns to something else. We will do that in a second. I am then, like I said, leveraging this climate model.jl for a couple of different things, but here I'm also using it to avoid having to reload a couple of packages that are already included in climate models.jl, so data frames in particular, and CSV. So this is the post-processing of the output. We are getting the time series of the positions, putting that in a data frame, and then outputting to a CSV file, right? So then the plotting reloads this file and just displays. Okay, so I'm going to do a quick change of this number of time step. So this is 100 time step. As you see, well, there's only so far you can go away from your origin point if you do 100 steps. If you go to, say, 1,000, all of a sudden, the map expands. Let's keep going. This is 10,000. Maybe I'm not going to do 100,000 right now because you will have to wait, but this should scale up quite easily. It's a simple algorithm. And so if we just rerun this, you see that you end up in different places every time. If you were to do this many times, you would see some sort of pattern emerge, but that's not the topic of the day. I'm just going to reduce this one tiny bit, make 1,000. No, I like 10,000. Okay. What else did I want to say about this? Yes, the climate models.jl interface. So this is a common interface to run models of different kinds. And what it does for you is it sort of packages this model run in a reproducible framework. So it starts by creating a little folder for you where everything gets copied and takes place, which also has a Git-enabled subfolder to keep track of the different operations in this sequence. So this is a very simple model. It has here, this is a view inside of the the folder that it's run into, you can just access that from the data structure of the climate model. In this case, it's a Lagrangian simulation, but so you see here that it has the CSV file. And then if I do this, I think should work. This is the Git enabled subfolder. And so the point of this subfolder is that I put the environment in there. And I also keep track of any change that's made to those files. So the point is that at the end of this, you should have in one folder the history of what you've done, and that enables you to reproduce the computation later, setting aside the randomness of this particular computation. So there we go. And so what this package enables us to do is that once you have, looking for my code here, where did I put this? Once you have formulated this data structure, basically you set it up and then you call run on it, and everything else happens in the background, creating the subfolders, running the thing, and so on. It also attaches to each computation a unique identifier, so you can distinguish between different model simulations later on. So this is something I created for myself to kind of embed my various workflows, and it's composable. So it's part of my digital twin framework, essentially. Any questions on climatemodels.jl or comments? Please do not hesitate to interrupt. This is a hands-on, so. No questions, so that means either that I'm completely unclear or that everything is transparent. Which is it? Go ahead.
I'm unsure why you included climate models in this demo. Can you explain a little bit more?
Yep, thank you. Yeah, so I included this in the demo because I guess two reasons. One was a good opportunity to describe it and to explain that it's a general framework that can be used for the rest of what I'm doing. And the other sort of simpler answer is that it was like that in the notebook that I already had. So I'm reusing a notebook that had that in it. And it's in fact one of the examples of the climate models.jl documentation that we're looking at. Yeah, cool. Any other question? Nope. Okay. Then we're going to go back to the ocean transport problem per se. And I can hide this. No. So this is a notebook that you should be able to rerun without data. Has anybody tried? Yeah, it works. Excellent. So we've already seen that you can change the number of time steps. So I don't need to say much more about this. If you rerun this cell, right, which we can do in this Pluto notebook with this button, you will see new instances. And so if you run a lot of these, what you will find is that the distance that you reach over a number of random time steps sort of converges on average. It relates to, or it's often related or expressed in terms of a diffusion rate, which is a little interesting in itself. And so typically these things kind of spread out as a Gaussian if it's just completely random. If you imagine that you would have an ocean current that would move stuff around, then you would see something different, which would be much more, which have a much clearer direction to it on the average. Oops. So I just want to rerun this one more. All right, so you can do this a million times and, you know, generate new examples every time. And then I'm going to close on this one after just showing you the log of the Git subfolder. So here we see that we have done the initial setup. I've backed out the parameters of the model. in this subfolder, and then the project.toml, the manifest.toml, and so on. So that's the Git functionality. All right, now, next one. So next one, we are going to do the global ocean circulation problem that I had announced at the beginning. But before I go there, I'm going to show you this one. So this is a different way of doing this. And in fact, this example is 1D as opposed to 2D. And it's meant to illustrate something slightly different. This is from this paper here that I've cited. What we do in this problem, so if you look on the left-hand side, you have the initial condition, and then what it converges to. And then on the right-hand side is the result that comes from this so-called Lagrangian particle tracking simulation. I'm going to explain why there's two different panels. But basically, we start from a configuration over this axis here, the horizontal axis, which you should think really as the vertical axis, probably, because it represents the ocean mix layer. So we're really talking about the vertical processes, although I plotted it the other way around. So the idea is we start from a situation where we have two layers and that are very distinct and completely homogeneous. Oh yeah, go ahead. Excellent question. Thank you for that. In fact, it's hard to find. See if I can find it myself. So this one, if you go to my GitHub profile, so this is github.com/GaëlForget, and you scroll down, you're going to find a bunch of different organizations. So one of them is going to lead you to the JuliaOcean organization. Within JuliaOcean, which I will describe a little bit later, you will find this notebook. So this is now github.com/JuliaOcean. This notebook is hidden a little further because it's a package that's in early development stage. So to find it, you go in repositories, and then you scroll down a bit, and you're going to find something called oceandistributions.jl. All right. So this is now github.com/JuliaOcean/distributions.jl. If you go in the examples folder, there it is. So it's something called onedimdiffusion.jl. Anybody has managed to find it? Yeah. So I'll remind you, this says you go to github.com/JuliaOcean/oceandistributions.jl and then examples. You will find this file called onedim for one-dimensional diffusion. Good. Sorry for that. I should have put it in the notebook folder in the first place. I just was a little late on doing that. Do you find it? Cool. Okie dokie. So now I'm back to this page, which is the notebook that's running in the container. It's using 3 packages. For some reason, I decided to use Unicode plots in this case. I don't know why. Could have used Mackie, that probably would have been more interesting. Unicode plots is, for those who have not used it, it's a little package that lets you display graphics within the terminal window, which is kind of nice because it doesn't require any other sort of library, or at least not an external pop-up window. More importantly, Statistics is just going to probably do a mean, and stochastic DFQ. So stochastic DFQ is one of the packages from the SciML organization on GitHub. So if I go there, I think I'm going to find this way. Yes, which I don't think we've mentioned a ton so far, but there is a very, very strong differential equation based framework, which is originally developed by this person, Chris Rokas, but has a lot of contributors and a lot of very good stuff. You also see some of our colleagues that are here. And it is now a kind of a broadly applicable framework. I use often ordinary differential equations. This is what we'll use, in fact, in the next notebook. But in this case, I'm using a stochastic ODE solver from them. So this means that we won't need to recode the random walk like we did, for example. This would be another way to do it, but I wanted to take advantage of the differential equation packages, which will also give me a nice segue to the next problem where I'm going to use it as well. All right. So there's going to be two models. There's going to be the so-called Eulerian model, sorry, where what you're going to see here is a little diffusion equation. And that is what leads to the left-hand side plot here. So if you just start from this sort of step function and you apply a diffusion operator on it, over time, it's going to smooth the contrast between the left and the right. This is the same processes of diffusion that you will experience pretty much anywhere. And that is happening anytime there is a kind of a turbulent fluid. Or even other processes. And so essentially what happens is over time, this kind of step function sort of flattens by just virtue of simply integrating this Eulerian model, which if you look at what I'm doing here is just taking a finite difference over a grid and then integrating that over time. And the rest here is just plotting and then, just over time step. So this is the sort of modeling we do on a grid, as opposed to the Lagrangian modeling framework, where we're going to follow particles. And so this here now is the one that uses the stochastic differential equation solver through this function. I need to remind myself what I did there. Yeah, I think I have a condition such that with this here, I'm preventing the particles that we're going to randomly move around from exiting the domain. And importantly, there is a second term in the equation that I'm going to tell you about in just 1 second, this one. So the main loop now, temporal loop of integration, is here in this function. It goes over a number of time steps. It solves for the pathways of a bunch of particles over time through the differential equation solver. It applies this little boundary condition, if you want to call it that, to keep stuff inside. Yes. And there is two sets of particles in this case. So the way that this is set up is, instead of working on a grid like we did before here on the left-hand side, we have the same initial conditions, but it's formulated differently. So it's formulated by having one set of particles with a certain property, of 1 that are going to be evenly distributed in this range of the x-axis. And similarly, on the left, we have a bunch of little particles that all have a value of 0, and they are randomly distributed over this layer. So we start from these 2 pools of particles. So what makes the step function now is the fact that they have constant values in each group. And that's where the other term comes in. So we're starting to move them around. And I'm going to remove this and see what that does for me. I should have done that beforehand. Okay, you see that the results has changed a little bit. And this is based on the averaging of positions. So now we are taking these 2 groups of particles. We have moved them around randomly in the range from 0 to, I mean, here it's 1 to 10. And if you take for each little part of this, the average of what you find there, you're going to find a bunch of zeros and a bunch of ones, right? The zeros are still kind of staying on the left and the ones still staying on the right a bit, such that we have this kind of gradient. But it is in fact rather different and wider than what you're going to see next when I add this second term. So what this second term does, and that's the point of the paper I was citing at the beginning, it represents I'm going to just wait for it to finish. There we go. So now this has collapsed, right? And this is, I believe, oh, I kind of messed up my plot, I think. This is kind of more lined up with the what's on the left. So what's happening now is anytime we have a collection of particles that are at the same depth level or the same point on the x-axis, we mix their properties a bit. So instead of them staying at 0 or 1, we kind of average out and we change their properties. And so this represents mixing at the micro scale. And so the idea here is you need to include this term and let particles that are near one another sort of interact with each other a little bit. So that's what we've added. We've added interactions between the particles. And so this is what this term does. And what else should I say about this? Not that much. The point was really to illustrate that instead of using my quick little simple random walk for my simple case, you can do a lot more with this by relying on stochastic ODE solvers, for example, that have a lot more processes represented in them and a lot more options. And this is one of the ways that we can simulate in a continuous way the stochastic parts of fluid dynamics. Any questions or comments about this example? I went maybe a little fast. No? Was that maybe unclear? So you can then, you should be able to run this this notebook without input again. And so far we have done 2 very simple cases that both have to do with random movements in the ocean or in the atmosphere or in any fluids really that are going to tend to spread out materials. So in the ocean, for example, if you have, thinking again about the plastic problem, if you put a bunch of plastic here, right, and you have random flow fields, they're going to tend to distribute out. We're going to now look at the other part of the problem, which is the more predictable component, which is that if you have a bunch of plastic and you put it in an ocean current like the Gulf Stream, it's going to go eastward, right? And so the mix of those two things is ultimately a good way to understand what's going on with that marine litter problem and this issue we have with the great garbage patch. There is a vertical component. There's other things having to do with the fact that unfortunately fish eats all of this microplastic. There is also evidence nowadays that a bunch of the plastic gets stuck not at the surface but somewhat below. And they also interact with the biomass itself. So if you have particulate matter that's falling down because biomass is dying or its excrements are falling to the seafloor, that might aggregate a bunch of the plastic and bring it down to the seafloor. So there's all sorts of processes that are quite interesting and in fact, still require a fair amount of research that I'm going to overlook here. But a good starting point is to think of the marine litter problem, or in fact, the marine ecosystem displacement problem as a combination of those two terms that are both horizontal. One is going to have a predictable non-stochastic component, which is following the flow fields. And the other is going to be this sort of stochasticity that's going to tend to expel and redistribute the materials over space. So now with all of this introduction and setup and having done the stochastic problems, we're going to look at this, which is what I announced in the first place. I'll take another little break here to give you an opportunity to ask questions or make comments or whichever. Anyone? Maybe I go back to the previous notebook before I change. Anybody has had success with this one or more question about this this particular example? Oh, I'm sorry for that. Is it because your Wi-Fi is completely off?
Yeah, I'm connected and then I'm out and then I connect again.
No, that's unfortunate. Hopefully you will be able to. So this notebook ultimately should not require Wi-Fi. Once you have just downloaded the text file, if you have Julia on your machine, you can also run it that way, right? So maybe I'll show that actually. Okay. So let me download this notebook. Well, actually, this gives me an opportunity to talk a little more about Pluto, which has some very nice features. We've already seen that you just have to plug in the file name. I want to show you this piece, which is quite interesting, quite useful to me very often. So there is an export function. If you're here at the top right, you click on this triangle and this circle, gives you the export function. The export function lets you do HTML, which here would be the end result of that. Lets you export, excuse me, the Julia file as well, which you can equivalently get from the website. Right, so that's the file. That's the notebook, the whole notebook in terms of code. So you can take that. And then we're going to do and you can do this with other editors. I kind of like VI myself. Okay. So what you just saw happen here, in fact, is sort of interesting as well, right? There's a lot of code, but there is very little that is, in fact, code you're using directly. So let me point that out once more. This is the structure of a Pluto notebook in its native code form. At the beginning, you recognize some of the codes we had, but very soon, once you go forward, you're going to get to this point where here you find this specification of the dependencies. And so this is stating that this notebook uses the statistics package, the stochastic DFQ package, and this Unicode plots thing. And everything after that, which is the great majority of the notebook, in fact, is the dependencies of the dependencies. So in this case, in particular, I'm going to assume that the vast majority of them come from this stochastic DFQ package. And it is because we have all of this included in the notebook that we are able to rerun it by just showing a file. Last thing I will point is, so there was 1,283 lines. Oops. Here we are at line number 220. So there's in fact only 200 lines in this code, in this notebook, most of which are markdown comments, like you see just at the top here. This is one of the markdown cells. And then there is everything else, which is the 12,000 lines, if I got this right. Sorry, the 1,200 lines. So 1,000 of this is just the dependencies, this documentation. And at the very end, there's one more thing to point out, which is the ordering of the cells. So as you might have noticed, sometimes I put my package dependencies at the end of the notebook because that's not what you want to present to the audience first, right? You can do this in Pluto easily because it keeps track of the ordering of the cells for running the code and for displaying it. So this is the order of the cells for displaying it. And otherwise, the code itself here, I'm going back to the top, is ordered in the proper way for just running the file. So I'm going to do Julia. Let me do something. I'm trying to wonder how am I going to get myself in trouble here. So let's see if I can anticipate that. This is going to pre-install the package that I haven't installed yet. So that in fact might be difficult if you don't have Wi-Fi again. But when you do the using command with the more modern versions of Julia, it lets you know when it needs to install something for you. And so here, I'm doing this on my laptop now. I didn't have the stochastic DFQ package, and so it's going to do that for me. It's going to install all of the subdependencies that I didn't have already. And yeah, I guess since we had not really insisted on that during the week, I think it's useful to go through it, even though it's a bit off topic from this session. This is, in a sense, what's happening in the background when you run a Pluto notebook as well. It does that, all of it in the background without you having to worry about it. But that is why there is a delay sometimes in the notebook starting, is if you didn't have those packages already in place, it needs to get them, right? And so here, there we go. I think I now have probably everything I need. It's going to then pre-compile the packages. There we go. And then we're going to be able to run the model. So include is just to include the Julia file. And it's going to run all of the commands that I showed you, the 200 lines at the top of the file. And hopefully, I didn't forget anything else, and it will complete nicely. I'll go back for 1 second to the web browser. So now here I am back in my original notebook that's running in the container. I just wanted to grab this, which is going to let me do the display in the terminal. There we go. So it's completed. All right, I'm back to my terminal window. And let's see if that works. There we go. So this is the, I guess I have 2 more plots in there. This is what I was telling you about the Unicode plots.gl package, which uses Unicode characters, encoding something, to make a quick little plot for you. And so it's not the high definition type of plots you will want to put in your papers, right? But this is a very kind of useful and quick way to operate anywhere that you can just have a terminal window, which in some cases is useful when you're on supercomputer or whatever. You might not want to be doing like displays because there are firewalls and so on. So it's a neat little option to have, and it can do heat maps as well. There's a lot of nice functionalities. And so here you sort of see the same result we saw before, right? With the 3 curves and the other one. So I realized that I sort of launched in a tangent based upon your question, but I hope this was useful. Yeah. And yeah, it lets you know that if you want to take one of those Pluto notebooks and run it in a kind of standard Julia way, you start with the using commands to install your packages, right? And then you can just include the file and it runs for you. Any questions or comment on that?
Just use import and then the path to the to just use the import.
Include. Yeah.
And then the path.
Yeah, you need the file there, and then you include and just the file name. You know, I was the import is also something in Julia. So import is a way to say import a package. So say I probably have CSV around. No. So import is different from using. Using is kind of the more Julian way, which is going to export functions into your environment. Import is more the Python way originally, such that you're not going to have access to the functions that are embedded inside the package with providing at the beginning the package name, the function name, or the data structure name, or whatever, but it all stays inside. So this is kind of useful sometimes when you have different packages using the same function names and so on. You can get into conflicts if you export all of them. In fact, we've seen a couple of cases like this between the, I think the rasters package, was it, or the meshes package and the Mackie package that have kind of the same function names. So that's kind of a useful thing to know about, import versus using. And the other thing I'm going to show you here, because I don't think we've kind of covered that and it's useful for people who start, is the different the different terminal modes. So if I go back in front of this line, right, and I just hit question mark, now we are in the help prompt. And that's going to give you the help of the function. So this is something you can do for any function that has a docstring to access the help and the directions immediately, right? And gives you sometimes examples like this. But in this case, you're going to create a data frame and so on and so forth. Another thing that I might highlight is this with the semicolon is the shell mode. So now you're back in your kind of standard Linux way of doing things. You access your file. So for example, this would be looking that the file is here in Linux. If you want to do this in Julia, so you go back to the beginning of the line and you type escape to go back to the normal mode. Maybe not, so you delete, not escape. So now if I do that, that's not going to work for me. However, there's a Julia function that does sort of the same thing, which is going to be isFile. So this is a way to do a lookup for a file on disk, the Julia way and the Linux way. One more, the package manager mode. So the backward square bracket package. Here you're going to be able to see everything that you have installed. And you do that with the status shortcut ST. So here you're going to see that I'm using Julia 1.8, that I have started a lot of work in 2019, and it's not finished. That I have a lot of different packages in there, including the one that I've just installed. Right? Again, you get out of there by doing delete, and you're back to the normal terminal mode. So Julia is very fluid like that. You can, within your terminal window, or you can do this also in the Jupyter notebook. In fact, you can access different components of your workflow, which I find is really nice. So enough about the terminal mode. I think all this. Okay. Unless there's any question on this. Was that useful to remind people of this? This is kind of a little bit of the beginner session that we sort of maybe didn't spend enough time on. And I guess another of my tangents. Okay, so finally, we're going to go to the global ocean circulation problem. And let me do something quick to see that it's running as I want it to run. Yeah. Okay. So we're finally going to use my individual displacements.gl package, which inside uses the differential equations package that I just demonstrated in the 1D case, but not stochastic. So this notebook has this nice little table of content, which in Pluto is extremely simple to create. It's part of the Pluto UI.gl package. And you just put table of contents and I think parentheses and you're done. Lets you navigate. So I try to do that in all of my notebooks when I think of it. We have here just a plotting function. We don't need to look at that extensively. I want to find my packages, which are going to be maybe at the top. Oh no, next one. Okay. So the packages that we're going to use here. So individual displacements is the main computational engine for this. I'm going to use Karomaki for visualization, Pluto UI for the interactivity and the widgets and all of that. And then the last two, Ocean State Estimation.gl is a package that I created to incorporate easily these NASA ocean circulation products that I was telling you about at the beginning. So ECHO, this estimating the circulation and climate of the ocean project, generates files that can be a little hard to handle sometimes because of some of the elaborate grids that we use to solve for the ocean circulation problem on the sphere. I mentioned that a little bit in one of my earlier presentations. And MIT GCM tools is brought in also for the same reason of it's useful for the output that I'm using. But if you were to use, say, a simple lat-long grid flow field that you find somewhere, say from the satellite, from the same type of things, for example, that we were looking at with Andre the other day, you can get, from the satellite, you can get flow fields for the sea surface. I'm simplifying. You could sort of, you wouldn't need those two, essentially. So the three that are really more important to this presentation are those three. And this is a bit of, convenience code for making things easy for me. So now we proceed the way that I have announced it in the slides. We are going to set up the flow fields, which is here. So I have a little function to do that. It returns data structures that are going to be providing the flow fields. I think it's P. Has that in it? Yes. So this has velocity fields at 2 time steps, 0 and 1 for simplicity, but really they can be, this could be a month between the two. In fact, it is a month here. So this is, say, January and then February. And 2 components, because this is a 2D problem. So U and V for the 2 components that can be eastward, northward, but they can be whatever. And that's what this mesh arrays package sort of allows you to do. And then there's going to be a function that is embedded in there and a time period. So this time period here should correspond to a month, if I'm not getting myself confused. And so this formatting of this data structure is the first step. That is what's going to allow the rest of it to follow in a very simple way. As you see here, it says F mesh arrays 2D, and that's because I'm doing a 2D problem. And instead of using a regular gridded flow field, I'm using this somewhat more advanced way of doing things with mesh arrays. But there are other variants of this. So there is a F, I think, just array 2D, which is for a plain array, the way you would most commonly experience it. And there are 3D versions of both of those things. So depending on the example you look at in the documentation of individual displacements, you will be using one of those 4. And we can do more if there are other array types that we want to support. So that's the extendability of this package. Since I'm at this, I will also mention this other thing here, D, which I use to carry around ancillary variables. So you don't have to worry too much about it. I'm mostly looking at it to remind myself what's in it. Yeah, so I have grid variables in there, and I have, these are temperature fields. So these are actually kind of interesting. That's where you will carry around the extra variables you want to diagnose from the simulation later on. And the rest you don't have to worry about too much. A lot of this is just bookkeeping. This function is important because it's the one that's going to tell the program how to update the flow fields when I go from one month to another. Okay, this is that. I can get rid of this. Oops, whatever. And as you see here, there's a little bit of indication that this is this echo program that generated the flow fields. There's a path that is interesting to notice. It's a technical detail, but there's a way that Julia lets you download files on the fly. There's even more than one. There's something called artifacts, and this is the scratch spaces approach. So what happens in the background when you run this notebook is, if it does not find the files, it downloads them automatically. If you are here today trying to run this notebook, that might get you in trouble because the download rates are slow. So sorry for that. You might have to go back to this notebook later on to run it in a way that will be more convenient. I pre-installed everything on my container so that I could just demo it for you. The notebook itself is called, oops, not what I want. The notebook itself now you can find though here, if you go to this notebook subfolder, and you go down to individual displacements, you're going to have the notebook right here. So this is the one that's called global_ocean_circulation.jl. The first example we did should be this one. So this is going back to, actually no, this is a different case. So I have all of my examples from the package documentation here, and there's a three-dimensional case. There is a case that I call solid body rotation, which is a sort of a, what do you call that? A vortex type of model. So it's just something that rotates around and sinks. It represents a process in the ocean that's interesting, but I'm going to just skip over all of that. And the rest is just glue code. A lot of the notebooks that I've shown in previous sessions and afterwards are in here. They have been installed directly in the container, in the image. So you should have them regardless of everything else if you download the Docker image. Now, back to this. I've done this part. I can remove this cell, which is kind of in my way. So in Pluto, again, you can delete a cell that you don't need. You can also disable them. At this point, we have defined the flow fields. This that you're seeing here, oops, sorry, is the next step. So once we have defined the flow field, we want to define the individual's data structure. So that's the one that's going to carry not just the flow field, but also the particles that we are then going to be tracking. There's a little bit of Unicode here to make it look funny. I kind of like it, but we can do without also. And what you're seeing here is the display of this data structure. So this is just the visualization, a quick way to see what's in it. So here we have 500 particles. This is the name of the solver, ultimately. Same here, and this is the post-processing function. And again, this is my flow fields data structure. So once that is set up, so we've done the flow fields and then we've set up the individuals that we're going to move around with the flow field, then we can run. This is the model run. So here we specify the time step, the time period, which I'm just grabbing from this data structure that I had. And that is the command line to do the integration. So it has this bang symbol here to indicate that it's going to be mutating the data structure I. We have mentioned it, Simon did in the beginner session. It's just a notation. It's not something strict, but most people try to put the bang to indicate that something is going to get mutated by the function. And this little integral is Unicode. That's where I kind of like Unicode. It really speaks to what the function does. Underneath it, there is a function. So if I do this, I'm going to be able to show you that. I think these are the methods that are behind this, and they are called, I guess they are called the same way. So there's 3 of them. This is the first integration. And then we're going to do a time loop on that. So there is in this package, in this example, I've sort of rearranged this in this way. I've created a new function that's also mutating that updates the time period. This is what's going on here. Replaces the flow fields that were for the time step 0 and time step 1, because we're entering a new time interval, so we need to replace those to the current month. This is a good place to say that you can also do this backwards in time. Here we are doing forward in time. And then this little function is something I wrote to randomly reset a bunch of the particles as I go. A very, very crude way of accounting for the fact that I don't have the stochastics term in there, so that it doesn't completely collapse on the same point. And then again, just the time integration. In this case, I can omit the time period because I'm starting from the very beginning of the time interval. And so it's just going to do the whole time interval. This step function, this step bank function, I can then put in a loop here. So this is the way that, a simple way to write a loop. It's a little abstract. We could write it differently with the for at the beginning and stuff in between. But this is essentially the same thing. There's a number of years and a number of months. This little thing at the end is to add the longitude and latitude to the output so that we can visualize it. And so that's the whole computation is those 2 lines, really this first line. So that's where the power of sort of Julia data structure really comes in, is it lets you write stuff in a way that's very condensed at the end, because you're leveraging a lot of native Julia features. This is the output of this simulation. So it shows X, Y. You don't have to worry about this component. And then temperature. I'm not sure why I don't see the longitude and latitude here. Should have that too. Yeah, it does. So there's a couple of variables that are not displayed. That's probably just because my font is, I don't know. I'm surprised it doesn't show them. But so in this, you have the identifier of each particle. You have the position in the grid space. This is just an index for the tile of the domain. Yeah, go ahead. Okay. We are running on the monthly climatology. Yes, that's yeah. So I'm going to circle through. Yes. So the question was whether I'm using kind of an annual mean climatology or a monthly mean climatology. The answer is I'm using a monthly mean. Or if we are using decade long, and then we do the climatology. You can do it either way. Yeah. It's just the way that you're going to reload the things. So indeed, we're using the monthly climatology here. So I'm going to use it in a circular fashion. So that we're going to go January, February, December, and then back to January, the same as before. If you have a data set that has year-to-year variations, so a time series like you just mentioned of say 20 years of data, where there is January 1992 in my case, and then all the way to December, and then February, January 1993, etc. same principle. The only difference is, you know, the way you read the files. That's it. Yeah, exactly. Thank you for that. Time, and then longitude and latitude. So this is my little data structure to store the output as I go. For each month, I put stuff in the data frame so that now I have the whole time series at the end of that. And I can put everything in a nice CSV file. Ah, there goes my longitude and latitude are showing up now. And so the visualization at the end, I have a little function at the bottom that I can show you. But mostly what you're seeing here is a short simulation. And so each of the red dots might have been the initial position, and each of the stars is the final position. So over 1 month, we've just computed the way that each one of those would have moved according to this climatological large-scale circulation. So each of the dots, if you think, can represent a bunch of plastic put in the ocean, right? And we're going to track it here in this case for just 1 month. And let me change this parameter, which I think is maybe here. Nope. So instead of doing that, which is this 1/12 of a year, I'm going to do 2 years. And I'm going to go back to the visualization. So this is still computing. And then it's going to show me the result. And remember how close the particles look like at this point. You're going to see something slightly different next. So this is the 2 year of computation and the whole sequence. That's taking a little while. There you go. You saw what happened? Now there are the black stars, which are the final positions, now I'm sure, have collapsed a little bit towards those lines that you see. And they would have collapsed even more if I had not sort of done this resampling of the domain. And so what is taking place here is that over that 2 year time period, the little patches of plastic have followed the ocean currents near the sea surface. And it so happens that near the sea surface, that flow field is convergent to certain regions. I've mentioned that in the slides at the beginning. And that is why the great plastic patches exist and the plastic tends to concentrate in certain regions. So if I go back and I do, oh, I didn't let myself put more than that, okay. Whatever, I'm just going to do a few less. Show you another example. So you can change the parameters and rerun this thing. This should scale fairly well, depending on your memory. You can do 10,000 or whatever. The ODE solver is really what brings the speed here, aside from my having to read in files and so on, which can induce some latency. So there we go. Now we have a few particles, but you sort of guess the same pattern. You have questions on these simulations or on the? Speak up. Can you make it for you? Sure. It's going to lag a little, maybe, but I will do that. They should, like those in the east, should progress more interior. I don't know. I'm just. It's possible. Let me do that. I'm also going to remove. Sorry. Where did I put this? Right. I'm going to remove the thing that sort of resets particles at the beginning because it kind of blurs the picture a bit. I just need to remind myself where I've put this function for stepping forward. Yeah, there we go. So I'm going to comment out this little thing here. I'll leave it open. And I'm going to go here. So as a side note, I'm going to make that the default. This way it will run it for me. So this is going to be running now. What you're looking at right here on the screen is one of the markdown cells that is where all of the widgets above are included. That's one of the things that I love with, in fact, Mackie and Pluto, is you can define widgets very easily. So this is the one line that defines the button for the depth level, right? Because there is, in fact, a button for the depth level. This is the one line that lets you select, include a widget for selecting the duration of the run. And this is the one line that lets you select for the particles, the number of particles, I should say. Oops. Okay, I've done very few, so I'm going to do more because I went back to 10. I'm going to do a longer calculation. And instead of putting 10, I'm going to go 1,000. Why not? So now I'm doing what you suggested, Andre. I have increased the duration to 4 years. And I have increased the number of particles to 10,000. So I expect that we are indeed going to see more convergence of the particles in expectedly these specific latitudes that we have already noticed, and sort of more towards the eastern part of the basin, which I think is what your question really was. Right? So this is going to run maybe a few seconds because I increased the number of particles a bit and it's longer. So while this runs, maybe I'll open it for another question or let you follow up. Anybody? Oh, there we go. See, fast. Yeah, so indeed, now that I have removed this kind of stochastic term that I arbitrarily introduced, the flow fields being very laminar in this climatology, things collapse very hard on those lines. And so this is the way that the global plastic patch, garbage patch, might look like if there were no turbulence. Oh, thank you. If there were no turbulence in the ocean, right? That's the idea. And so, yeah, there it is. I don't know why it's running a second time. Did I click twice? Maybe I clicked twice. Oh, that's unfortunate. So I'm going to do something else since I'm here at this point. What do I have? I'm going to change the depth level. Because I have mentioned before, we are doing this at the sea surface, or near the sea surface. Let me show you how things change when I go back to my 300-meter depth case that I was telling you about at the beginning. This is not going to be super interesting with the 10 particles here, but I will again change that to make it a lot more in a second. So what you are going to expect to see is that the particles are going to move at this 300-meter depth level much more like the Gulf Stream does, because now the influence of the winds are much less at that depth. The reason why the surface levels are so different and they converge so much is because the winds are creating this pattern and moving stuff near the sea surface towards certain latitudes. So let me go back and increase the number here to again, where am I? Let's do 500. So now we should see something that starts to resemble the ocean circulation at that depth, assuming I didn't, make a mistake along the way. Any other question? Comments? Yeah.
Are you placing the dots randomly? Hello. You place the dots randomly on the map, right?
Yeah.
But in reality, the plastic could not be randomly placed. So some of that big chunks of plastic in the middle of the ocean not exist because the initial place will not exist. You understand my idea?
Yes, I do. So you're correct on that. Ooh. Okay, I'm getting myself in trouble. This is now a much shorter computation. But yes, you're correct. So correct, and at the same time, it's a little more complicated than that. So what happens is, if you wait long enough, regardless of where you put the particles, they basically end up in the same spot, more or less. And that's because everything is connected. They are, I'm oversimplifying a little bit. But if you wait long enough and you put something in the Gulf Stream or a bit further from the Gulf Stream, you might end up in the same spot. That's going to still depend on the basins, right? So if you put stuff next to Japan, it's not necessarily going to end up in the plastic patch of the Atlantic. It might end up in the Pacific, right? So that is for the sort of the long time scale. They're going to converge eventually. But you're completely right that, the beginning of the simulation is very dependent on where you put the particles. And so when you want to go and study these problems and draw conclusions about the real world, right? The way that you would do this is you would not initialize stuff randomly, but you might put a plastic mass next to each river outflow, river mouth, that would correspond to an estimate from, from reality. And if you do that, which is what a lot of the projects like the Ocean Cleanup Project does, for example, then you start to really be able to talk to who is responsible for the plastic and what their contributions are, and have something more realistic. But it's a very good question. Thank you. All right, my simulation here is just too small, so I'm going to, I don't know why it's doing this to me. All right, let me just, doesn't want my default somehow. Actually, we'll do that. And I'm going to do 4 years. Oh, there you go. So now I should be forcing it to do what I'm telling it to do. And then go back here. I'd like to see my Gulf Stream at some point. We'll see. Anything else? Any more questions? Comments? Okay. So since I still have the floor, I will say that we also have other frameworks in the broad, in the overall Julia software ecosystems that. Oh, I see. Sorry. Every time I reinitialize the cell, it sort of overrides my choices and it puts everything back to the defaults. So this is level number 4, which is close to the sea surface. And all right. I'm hoping to get there. I was saying that we do have other packages that let you, for example, do Eulerian simulations. So you provide a flow field, and instead of advecting particles, you can do a tracer experiment, a tracer release experiment. So that is this kind of passive transport framework. Some of this is in the Julia Ocean organization. There is also, at this stage, a model called oceanigans.jl, which is developed by some of our colleagues at MIT, funded through the Clima program. And that there's computation of the flow fields themselves. So if you want to model the ocean, one of the first things that you might want to do is simulate the ocean currents themselves, which I did not cover in this. We have a lot of climate models that do that. We have observations from the satellites that give us flow fields. We also have now Julia packages, like Oceanography that can do that for you natively based on just an initial condition and a set of equations. In fact, Oceanography is a re-implementation, if you like, in Julia of the MIT general circulation model. And so they are sort of not, they don't have quite the same features, but they are two examples. I think this, oh no, I thought you were raising your hands. That's okay. So there's 5 minutes left. Any more questions? Maybe, I don't know if we're looking at online questions or. So I did not manage to set up the computation I wanted to do. So this is still the surface circulation that you're saying for some reason. Maybe I hard-coded a number somewhere. But you can use these tools to look at the two-dimensional problem at different depth. You can also do the three-dimensional problem with the same code and the same notebook by just changing the depth level to the value 0. That's in theory, but I'm not going to try because I've already failed a couple of times. And so this is a package that lets you do three-dimensional as well. And you can also find in the documentation of individual displacements of gel examples for the atmosphere. Exactly the same idea. Typically, you want higher frequency than a month for the flow fields of the atmosphere because of the storms. But same code, same principle.
It's possible the model taking into account the plastic that sinks, or you're just taking the account the constant levels. The plastic is always on the same level.
Yes, very good question. So I was just saying you can do 3D, right? So first of all, you can provide three-dimensional flow fields, right? And in this case, you will let normally the particles follow that. So that's the first part of the answer. But the second is you can also change the, I guess, the advection kernel, meaning that instead of just taking the flow field to move your particles, you can do what you want with it. So you can add a term that's just sinking, right? So even in a 2D case, you could do that. You could have a two-dimensional flow field that you integrate over space, but you have a sinking term that tells you that at some point you go below a certain depth. And maybe at this point, you'd say that that's not in my layer anymore. That's a package that I'm also using for things like simulating the behavior of Argo floats. So you can add in the advection kernel a term that represents an active control by an operator, right? So you can make the Argo floats, for those who have not experienced that, buoys that we put in the ocean. They have a certain floatability that we can specify. And so they're going to drift typically at a depth level of, say, 1,000 meters. And every 10 days, they're going to go down to 2,000, back to the surface, measure temperature and salinity along the way, stop there and transmit data to the satellite, and then cycle like that again. So you can build all of this in and do simulations of observing systems this way. And if you start adding some of the stochastic term and so on, you hopefully can reproduce kind of a realistic behavior of the Argo network. All right. Time for lunch? No, one more question.
Thanks, Gail. Super interesting.
Cool.
When you run the simulations with Argo flows, I'm guessing you have very different levels of accuracy.
No, not necessarily. The fact is that the depth at which the floats have been set to drift, this 1,000 meter depth, is a place where the flow field is in fact fairly laminar and fairly predictable from climatology. Also relatively slow compared to the sea surface. And so that means a bit of an easier problem than maybe at the surface. So my laptop just, it's time for lunch. So yeah, but you want to test that for sure. I mean, it's not an easy problem to do it, in a very realistic way. And there are other colleagues that do it better than me at this point on that, actually.
What's the accuracy level?
I don't, honestly, I don't have a number to give you, and I have not done this in very recent times either. But we can definitely look into that if you're interested, and then set up calculations that we can compare to the real network. In fact, it's a segue a little bit to my my contribution to the presentation with Alex this afternoon. I'll tell you a little more about how to access the real data sets from Argo and from other projects that give you the real life scenario that you want to test your model against, right? And so this is kind of where I'm going with this, is trying to get those two things together, and then, you know, train some neural networks, some estimation methods that might be better, Bayesian something, and sort of get into those questions, and be able to simulate, hopefully, any observing system. Another example is, you know, a mooring, right? A mooring is something that's put with an anchor to the seafloor. And it has a floatability that basically makes the cable sharp and tense, I guess, so that it doesn't move too much. But nevertheless, the tides are going to move it around, the waves are going to move it around, and so on and so forth. And so you could use these tools to look at that and try to simulate the way that your mooring behaves, just with a different set of equations and advection kernel again. So it's a very generally applicable framework. The accuracy, typically you get there once you put some amount of work in specifying all of the equations as precisely as you can, the stochastic terms as precisely as you can, and so on. Does that address it?
Yeah, thank you.
Yeah, all right. Well, thank you all for your listening to this, and see you after lunch.
So very right, time for lunch. We'll be back at 1. For those who are following online, yes, we'll be back at 1. See you.
Alrighty.
second part of the fourth day of this workshop. And we're now starting with the hands-on sessions. There will be two parallel sessions. The 1.1 simulating oceanic pathways of, Julia showcases in oceanography with Alexander Barth and Gail Forget will be here. And the 2.2 machine learning with geospatial data, what can go wrong, with Julia Hoffimann will be upstairs. I will go to the room upstairs with Julia for those who want to follow me. I'll see to do it. Just going to present Alexander. So, Alexander Barth is a researcher working at the University of Liège in the Geohydrodynamics and Environment Research Group. He did a PhD on nested numerical ocean models and data simulation. Currently, he's working on variational analysis schemes for climatologies and neural networks to reconstruct missing data. Since we'll have the same two speakers and the same topic after this first parallel session, you can then be free to continue at 1:45 with the hands-on session.
Okay.
Okay.
We'll follow up. Yeah.
Those who want to come with me. Thank you.
Thank you. And a bit of housekeeping. So for the hands-on session, I passed already yesterday this USB stick with the notebooks and the data. So if you did not have it, you can raise your hand and give the USB stick so they can copy it now. But there are two folders, one with Docker, one without Docker. Okay. But it contains exactly the same thing, except the with Docker contains the Docker images. So you just have to use one. You just have to copy one. Okay, so welcome everybody. I will talk today about some showcases of Julian oceanography. So I will talk about different topics. We'll talk about a little bit of numerical modeling, data analysis, and machine learning. So these are the three main topics of my talk. And so concerning numerical modeling, most of numerical models today are still written in Fortran. But I would like to argue that Fortran and Julian share many similarities in the sense that they have been made by the same motivation. In Fortran Fortran comes from formula translation, so the main objective was to translate formulas into code. And what I find quite interesting, for instance, in one of the original Fortran papers, they give you some snippet of Fortran code to call the root of a second-degree polynomial. And I think it's very surprising that this is almost already valid Julia code. Yeah? So they always thought about having the function just defined in one single line. They also think about defining types of functions, not so, it's get in your way. And so it's almost valid Julia code, except for the exponentiation with the hat. But it works for different reasons, right? So in Fortran, it works because ABC, so they are implicitly declared as single position. So it is not as advanced as Julia, where you have type propagation. Okay, and it will only work with floats, with single position floats. But now we know that the implicit declaration was maybe a neat idea at the time, but as a source of large problems later on. Okay. So what I did here is a very simple showcase of solving the two-dimensional Navier-Stokes equation, as you see here, and we simulate the flow of around an island. So here you can see what you see here. The structure is called the Karman, the von Karman street, with von Karman, and so that there are certain numbers of eddies which are generated in the wake of an obstacle. And so initially I made this simulation with PyPlots, but I then found out that Mach is much faster, and it allows you to do some interactive stuff like moving the target around, and so what I find remarkable about this, to solve the Navier-Stokes equation in this simple case, essentially just takes about 100 lines of code. It's really compact. And when you do the same thing in Fortran, Fortran is not much longer. We have all the type declaration, but you can also write it similarly compact. But it's a bit longer. But the Julia code is actually quite competitive to the Fortran code. So it's all explicitly loops without bound checks, and so the Julia code is actually even a bit faster than Fortran. Okay, here I use the G-Fortran compiler, so other compiler might have different runtimes, but it's really the take-up messages for numerical modeling where you have some when you want to have some high performance code. Yeah, Julia is really quite competitive and even better than Fortran in my opinion. And but Julia really shines on the flexibility. Okay, so this code was written just for two spatial dimensions. But what you can do also in Julia quite nicely is you can generalize your code in arbitrarily high number of dimensions. So I don't know if you have ever seen a 3D high dynamical code. You see a lot of code which is copy pasted. Okay, that is my momentum equation, the X direction. This is my momentum equation, the Y direction. So you have a lot of repetitive codes in these models. And in Julia, using Cartesian index and sometimes macros, you can all avoid this repetitive code. So going from a two-dimensional dynamical model to an n-dimensional, n can be 2, 3, or whatever. It actually is not much longer, and you don't sacrifice performance. That's also so. It's the runtimes are essentially the same. So even if it's very generic, you don't sacrifice the performance. Okay, this is just a simple showcase. But if you're really into ocean models, so maybe you should look maybe into these packages. I'm aware of like Oceanography from the Cremer project, as Gail also mentioned today. And we have also seen Milan this morning talking about shallow waters. And there's also IBEX for biogeochemistry modeling. So for the other part that I want to touch is about data analysis. So of course, the very first thing that you need to do is first to have the data imported into your Julia session. And I believe for ocean data, the problem is that the typical ocean data is really heterogeneous. So we have a large suite of instruments in situ or remote sensing, and they have all different characteristics. So the data in the ocean is really heterogeneous. So we have point clouds, rasters, and so on. And we have to have also flexible metadata format to capture all this diversity. And so for this reason, I think NetCDF is quite well posed to tackle this. So it comes mostly from the modeling community, I would say, but it has been by now also widely adopted for remote sensing and in situ observations. But we have to remember that NetCDF is just a container format. So it means that how the NetCDF is structured, that's another question. And therefore we have the CF conventions. And so yeah, most of the data is currently distributed in NetCDF, luckily, and there's some push. I would say there's also some push towards using NetCDF, but I have to say also some other formats gain attraction, like ZAR, for instance, which are very interesting as well. But the NetCDF library can by now also read ZAR data. So NetCDF has become kind of NetCDF library has become kind of multi-format packages where you can read proper netcdf files. You can read data from OpenDub server, but also you can read ZAR files within the netcdf, and even the old CF files. But there are different packages in Julia to read this data. I think the first packages is the one from netcdf-gl, and it's used directly as a C library, and my NC datasets also uses the C library, and then there have been several packages which have been built on top of these packages, like the Rastos-gl that we have heard today from Raphael, which uses NC datasets in the background, or Yaxaway from Felix, and, which uses netcdf-gl. And there's also another package that I recently came aware of, which is called netcdf. I think it's quite interesting to see all the libraries which depend on netcdf. So the C library is in Julia is called netcdf-gl and -gll for Julia link library. So that's the C bindings of the library. And so any other libraries which needs to load netcdf files either depend directly or indirectly from this library. So if you want to have a higher resolution version of this graph, you can just click on this link. It will download an SVG file where you can zoom, where you can more easily the packages. So just to orient yourself, what is in green here, that's the C library in netcdf-gl. And all the other packages which depend on it are linked with a green arrow. That's the netcdf library from JuliaEO, and that's the NC datasets library for reading netcdf files. So you can see this quite interesting graph of how the different packages depend on each other. And what I find also interesting is that actually some packages depend on both. And there's actually no problem to require both packages, actually, because under the hood, we're all using the same netcdf C library. That there will be not a problem to actually use both. And this is also something that I like a lot in the Julia community. This is this kind of standardization that we decided that all C extensions, has to go to a special repository, which is called Yggdrasil, but that's not important. But we have standardized on all the C libraries, that we all use the same C libraries. Okay, and this is the main reason that in Python we have pip and conda, I think. So in pip this is not standardized, and in conda they actually try to say, okay, now we have to use all the same libraries, the same C libraries, otherwise our package won't work together well. Okay. And so now I will talk a bit about the different tools that we have developed to work with ocean observations. So one of the maybe the first tool that we developed, and still our main tool, it's called DIVA, which stands for Data Interpolating Variational Analysis. So essentially a spline interpolation of in situ data. So you have some measurements, and you want to say here you have some measurement of the ocean, and you want to interpolate it and have a gridded field out of it. And there are some parameters that you can choose. Essentially, you can choose a correlation length, which tells you how far away you want to propagate information. And you can choose also the accuracy of the observations. And this was actually, I had a workshop in November last year in Chile, where we teach some students how to use Julia and this package to create some analyses. And yeah, we make a kind of challenge out of it. The idea was that the students need to choose the optimal placement of some observations in order to get the most accurate field out of it. So should you have any questions, really don't hesitate to just raise your hands. You don't have to wait to the end. But so just wondering, who has heard about DIVA before? Okay, thank you. Oh yeah, yeah. So the original tool was written in Fortran, and now we have translated to Julia. And the nice thing again is that the Fortran code was just limited to 2-dimension, and by translating to Julia, it gave us the flexibility to enhance it also to multiple dimension. That's why we call it DIVA ND, because it can work in higher dimensions. And so essentially what DIVA does is to try to find a field phi, which is as close as possible to the observations, DJ. And but at the same time, this has also to have small gradients. You don't want to have, you want to typically have a smooth field. And that's the second constraint that we're doing. Another problem that's you often have with, let's say, traditional interpolation approaches is that if you have the salinity, which is very different from one, like here, the Pacific, and from the Caribbean, you can easily have some values from the Pacific that leak through any island or physical barrier that should be present in the system. So by using the spline interpolation technique, you essentially it's very natural to take these boundaries into account. Actually, it would be even difficult to not to take into account. So you can easily decouple domains using this. And another thing is by using Julia, it became very easy to add additional constraints. Okay, and they can become necessary when you have, for instance, when you're not just looking to scalar quantities like temperature, salinity. When you look to observation of currents, you know that the zonal, meridional, east, west, north, south component of currents are not independent from each other. So they are linked dynamically. And this has become very easy to incorporate by using Julia. So essentially, you know that, okay, it takes a lot of energy in the ocean to move water from beneath to the surface. So the currents are mostly divergence free. Not exactly, but the divergence is relatively quite small in the ocean. And so if you have a velocity measurement and you want to create a gridded field from it, your gridded field should also have a low divergence. And here, this is some. If you want, this is on this link tinyurl/demo radar. There is a Pluto notebook running on Binder, so it takes about 2 to 10 minutes to start, where you can just play around about how it works. So I have it open as well. So typically when you have, so in red is a hypothetical measurement, okay? So when you know at this location the current is flowing in this direction and you want to see, okay, how is the current flowing in my domain? And should you have a closed domain, then you know that the currents, the flow has to go somewhere, okay? So, and by using this divergent constraint, you can actually see you would naturally have this recirculation. So if you ignore the divergent constraint, you would see, okay, it will just flow in the same direction that you have to measurement, but then you will have the problem that, okay, you're not, the water has to flow somewhere. Yes, for sure.
This is an analytic solution.
No, that's actually the solution from DIVA using the constraints, but it's a synthetic case. So this is actually computed on the fly by using the DIVA tool. So it's minimizing the cost function, saying you have to be close to this point, you have to be smooth spatially, but at the same time, your diversion has to be small, and then you get this solution. And I think this is, even though it's a very synthetic case, you can show even if you have multiple observations, your final solution will be just a linear combination of all these this kind of structure functions. Okay, let's continue. Oh yeah.
I saw a comparison of Julia Fortran. I would like to ask in terms of modeling the comparison between Julia and COMSOL multiphysics. If you have already tried working with COMSOL multiphysics.
No, I did not. I heard about COMSOL, but I did not try. I did not use it, so I cannot tell you how the. I cannot tell you about this. Sorry. That's a good question, but yeah, in the ocean we are mostly just having water, and so and I'm not working at this scale where you would need to interact with the atmosphere and having an air component and droplets and things like this. So unfortunately, I cannot experiment this. But it would be really a high benchmark to reach to have something, a multiphysics model in Julia. Okay, so in the last part of my talk, I will talk about machine learning approach. So one of the issues with LiDAR is that you have to know quite well a priori what's your result should look like. You should know it's typically, you should know the dominant length scales, you should know the correlation scale, you should know how accurate the observations are, you should know how strongly you should enforce the divergence constraint for velocities, for instance. So every time you add a new constraint, you add essentially a parameter which depends on how strongly you want this constraint to be satisfied. And so we would try to another approach would be to use machine learning techniques in order to estimate a full fit from sparse observations. So neural networks. So what we use here is a neural network, and they typically require a lot of observations. So that's maybe one of the reasons that there are different machine learning techniques, and neural networks are those who typically require the most data. And for this reason, we looked here at satellite data, where for obvious reason you have much more satellite data than that you have in situ observations. But in satellite data, obviously you have clouds, okay, and you don't have really complete fields either. And actually, the big problem with satellite observation is, well, typically what you would do in when you train a neural network, you would have a set of training images with cloud, and then the corresponding image without cloud. Okay, and then the neural network will just do the mapping. Image with cloud should map to this image without cloud. Okay, so you would have a lot of pairs with cloud and without cloud. So typically you would take a clear image, add clouds to self, and then let it reconstruct. Okay, so that's the basic idea where such techniques are implemented. And the technical term is called in-painting in other domains. But the problem with ocean satellite data is that you have so many clouds. So at any moment of time on the surface Earth, there's 70% of the ocean waters which are obscured by clouds. So you cannot really, so you would have really few really cloud-free things if you would go this route. So the main idea here was for us to let's try to start with a method which can deal with missing data from the start. So we have an image with clouds. We add even more clouds to it and try to reconstruct the image with no clouds. Okay. And so don't worry too much about the details here, but we actually steal the idea from data simulation from the BIOS rule, how to work with missing data. So typically when you assimilate observations in the models, when you try to correct the model with some observations, you don't need to have observations everywhere. And so essentially we took the same approach also here. And in the end, you can show when you want to combine different information which each have this certain uncertainty, you can show that you have to combine them. And if the errors are Gaussian distributed, you have to combine them by dividing them by the inverse of the error variance. Okay. So, and in this way, so this is kind of a rescaling approach. And this, if something is missing, we'll just say the error is infinitely large. Okay. And if you divide by something really large, you would just end up with a 0. Okay. But this is really a true 0. It's not a 0 that marks, wait, here is something missing. No, it really represents the fact that we don't know anything about this. Okay. And so this is the general structure of the neural network that we have. So I should say, initially we implemented this in Python, but by now we have luckily succeeded to translate it to Julia. So what you have as the input is your input startup images. Here is sea surface temperature, SST, and also the expected error variance of the sea surface temperature. So, but think of it, it's a given value where you have data, and it's just infinitely large if you don't have data. And since we're working with the inverse of these quantities, they're just map to 0. Okay. And the structure is called an autoencoder. But it's actually very similar to a principal component analysis or EOF. Just who of you has already worked with EOFs or principal component analysis? Okay, yeah, some of you. So the basic idea is with this approach, you compress information linearly, yeah, and you can show that the EOF decomposition is the optimal linear compression of your data, that you can still recover most of your initial data. So it's a lossy compression. So you take a complete image, for instance, and you compress it down to say just 10 numbers, 20 numbers. But these 20 numbers are really carefully chosen that you can reconstruct most of the image back. So that's the basic idea of a EOF decomposition. And what the autoencoder does is really, really similar. So you take a full image, and then you're doing some convolution operation, downsampling operation, and then you compress the image in a small subspace that you capture really the essence of the image. And from this compressed representation, you can get back to the full image. Okay. But the main advantage of neural networks here is that they can also capture nonlinear relationships. So we know EOFs or PCAs are optimal for the linear case, but for a nonlinear case, we don't actually know. And autoencoder can actually work with can also represent nonlinear information. And since this is a neural network, it's very easy to add additional features, additional input data to the neural network. So you can also specify longitude, latitude, and the position of every grid cell, so that the neural network can learn, okay, in this location, the temperature, even if I don't have any data, the temperature is typically high or low. Okay. And another thing which is quite important, in my opinion, is that the neural network is not only asked to tell what is the temperature at a given location, it should also tell us how confident it is in its temperature reconstruction. And I think this is something really, really important, because sometimes the cloud coverage are really large, so you would need to interpolate over a large scene. And if you're unlucky, then probably also the image before and the image after is clouded as well. So you have to ask, the neural network should be able to also tell us how confident it is in the analysis. Okay. And so mathematically, this boils down to a cost function. I won't go to into the detail, but essentially, since we have two criteria, we want to be as close as possible to our training data, and we want to have a reliable error. So there are two things that we want to optimize, and you have to combine these two criteria into one single criteria that you can optimize. And you can derive this criteria by just looking at the likelihood. So it takes a Gaussian distribution, and you want to maximize the likelihood of your training data. And so this is typically what you get from this approach. So this is the original SST on panel A. So there's the sea surface temperature in the part of the Ligurian Sea, in the Mediterranean. And you see already there are some clouds in this area. And what we do, we add even more clouds. Okay? So we add even more clouds because we want to know how good our method is. Okay, so these clouds, so only this data that you see on panel B is actually given to the neural network. And we ask it to reconstruct the full temperature. And then what you get is panel C. Okay. And then we can compare, okay, every time where we had additional clouds, like in this area, like here, how well did the neural network reconstruct it? So you can see that the sum of this feature, like this area with low temperature, was reasonably well reconstructed, but some details might be wrong. And at the same time, we get this error map, and this error map tells us essentially, okay, how accurate the observation, how accurate the reconstruction is. So most importantly, the error map depends on the coverage where you have actually data. So the dark blue areas have a quite low error because we had actually data there. But not only, it also reflects that in some areas the error is just larger because the variability is just high. So and this actually can be represented also. And the latest thing that we did with this technique was to extend it to unstructured data. Okay, so not all satellite observations are structured, like a sea surface temperature grid, where you have essentially a raster of data. Some observations are actually rather point clouds, like you have in altimetry data. So currently altimetry data is just a point cloud, and you have the data along tracks. Okay, and from these observations, from these tracks, yeah, we try to obtain a full field in return. Okay, and this is just this is a validation result where you see on the y-axis the original data, on the x-axis the reconstructed data. And you see actually quite good fit between the original data and the reconstructed data. And we also compared to DIVA, the other technique that I presented before. And the neural network gave some improved results, but not by too much. So DIVA still works quite well actually. But the main advantage, in my opinion, about this approach is that they can give a quite reliable error estimate. So what I show here on the lower graph is the predicted expected error and the actual expected error. Okay, and ideally everything should line up along the dashed line, so where prediction match the actual error. What we see, so the blue line is actually quite good. So it's actually just some factor which some constant factor which is an offset from the ideal line. Okay. So the method really tells you the interpolated fields, the altimetry at a given location, but also quite reliably can tell you how accurate this reconstruction is. Okay. And so this was maybe quite dense, I don't know. So some more fun projects is that you can actually capture, so Julia works also on a Raspberry Pi, and you can do some fun projects like building your own satellite receiving station. So some of the NOAA satellites actually send their data unencrypted, and you can just get them with a homemade antenna and what's called a software-defined radio. So you can hook it up to your computer and actually get the data when the satellite is flying over you. And yeah, so I use for this the toolbox, satellite toolbox, to get at one moment the satellite will pass over us, and then another package, app decoder, that I wrote that can help you decode the image. So, and then you see something quite nice images from the data that you can see from the satellite. Another project that we're currently working on is actually to get Julia on some devices to actually build, well, for students, build ocean drifters themselves, and then equip any ocean drifter with a Raspberry Pi, and which is connected to the cell phone network, and then just query repeatedly its position and send it via SMS its position. And then this works already. Well, the software works already. The hardware, I don't know. We still need to do it, but it's quite fun to see when Julia represents you an SMS. So that's quite fun moment. Okay. And so my last slide will be just to draw your attention that we have in May a Liège colloquium on machine learning and data analysis in oceanography. So it's not specific to Julia, but I think many of you are working in oceanography. I think we have also some people working on one keynote presentation from atmospheric sciences. So we interpret it loosely. So you're more than welcome to join. And the abstract submission is open until end of this month. Thank you.
Okay. Thank you. All right. Okay, so just a few slides to throw up this very nice presentation by Alex to highlight a couple other things related to oceanography. The first thing I wanted to say is to acknowledge that in the genesis of this meeting, another one happened a few months ago, and I wanted to show you this amazing group of people that were here. This was organized by Aida, Joe, and Kana, the symposium on advances in ocean observations in July. And I participated in this workshop, which happened here, right? And so a lot of the credit for the genesis of this meeting might go to them, in fact. So this was about the sort of envisioning new types of observation that Alex just discussed also a little bit. So there's the URL here, and I put the picture to sort of highlight also Katarina was organizing this meeting already. All right. Next thing I wanted to tell you about is just a little advertisement for those two organizations that you see the logos of here, called JuliaEO and JuliaClimate. They integrate with a lot of the other GitHub organizations that we have talked about, including JuliaEO and others. I wanted to say that, generally speaking, these are meant to be, I sort of created those, or one of the lead developers of them. And the way that I see them is as very much open-ended, that they are not tied to a particular group or a particular grant. I see that as an important factor in kind of projecting in the future. So anybody who is interested in contributing is very much welcome if you have ideas. First of all, we are always looking for feedback. So do not hesitate to open an issue to complain. Sometimes people are shy about that, but that's really important for folks who develop software to know what's broken. So it's been mentioned before. So that's one thing to, if you find these organizations on GitHub, I'm going to show them to you in a second. Do not hesitate to say, hey, this doesn't work, or it's missing this, or how about that? We are very interested in hearing this, right? And all I'm saying here is probably applicable to the other organizations like JuliaEO that have been mentioned, I'm assuming. We're always looking for contributors to both existing packages. If you find that some features are missing, there's always the opportunity for you to participate in implementing them. Or develop new packages if they are needed, right? Bringing packages like these and that we have seen into GitHub organization will increase the visibility of them. It's a way of building communities. So it's totally fair to develop things on your own account. I do that also on GitHub. I tend to move things to organizations when I think they're ready to be more inclusive. It's not too messy, essentially. Or some things I just keep on my side, but mostly I think it's very useful to put your Julia packages inside organizations. That's how you will find new contributors, for example, or people that will be able to point out that there's something broken because they'll be able to access it. I think a couple of things to keep in mind is it's important to stay modular. So we try to do little pieces that play together rather than huge things. And always have in mind that if you create software, you're going to want to maintain it. So it's good to start small and build test cases that are going to allow you to keep all of these things streamlined. And also, these organizations have membership. For those two that I can speak about, JuliaOcean and JuliaClimate on the right. We are definitely interested in new members. Even if you're just thinking of developing software in the future, you don't have any specific to contribute, you're welcome to ask to be a member. And by and large, I'm always happy to do that. You go back one. Yeah, I guess I just meant to say that I'll put the slide somewhere and they have the links to the two organizations. So JuliaClimate and on the left, JuliaOcean. I don't want to take too much time, so I'm just going to mention, to finish this session, some of the packages that are inside of JuliaOcean in particular, and have to do with data. So as Alex said, we have a lot of different kinds of data in the ocean, and a lot of them are sort of custom type of things. They're not like standard graded data sets. And so often we build interfaces, or we rely on other people's APIs to kind of interrogate relatively small databases. So we're gathering these things as we speak. The list that I have here are a few things that I created myself. As you see, they are fairly recent. And they include, in general, each one of them will include a package with its test suite and everything, but also notebooks. So in the case of my packages, if you go down, there's often examples, and in there is where you find the notebooks. Okay. I had opened my window here. I will have examples for you in the hands-on part. So I just went back to this part. So this is my own GitHub account. You'll find the organizations that I was referring to here. JuliaClimate, briefly speaking, if you look on the right-hand side here, you will see that, in fact, there's a lot of the folks that are here are already in the organization, and are in the other ones as well. So it's really this sort of social dynamics of GitHub that I'm trying to highlight here, and the fact that this is all very collaborative. The notebooks folder, I've already told you, is the source of the Docker image we're using, and it's kind of a central hub as I see it. But here we have a lot of different packages from members of this community, and we're looking for more. Julia Ocean, a bit more small at this point. There's these three members, Benoît Pasquier, Jean Wu, and myself. And there's a list of packages that have to do with ocean data, like I said. So in the hands-on part, I will highlight Ocean Robots, which is sort of an interface to a bunch of things like Argo data and Drifter data and so on and so forth. Argo data itself, I have a specific package for that because it's such a widely used framework, Argo, this program, that I think it's really worth having something specific. And then ocean color data is something about, well, ocean color data. I will just leave it to this, and we'll come back later in the hands-on if time permits to show you some examples on the screen. Thank you very much for being here and participating, and see you later.
Do you have any questions maybe for Gael or for us?
Sorry, I just wanted to know what is the framework that you're using for the neural network? I mean, you mentioned that now you have it in Julia, so just wanted to know. And
yeah, that's an excellent question. So I started. I tried both KNet and Flux. Okay, but when I started, KNet was ahead of Flux, and they were missing in Flux. So I used KNet, and but I have a branch which also works with Flux. So I'm considering moving to Flux, and so it already works with Flux, but it's slightly slower than KNet. But I see, yeah, the community is really railing behind Flux. So so maybe I should really make the transition and just use Flux. But KNet is one of these packages. It's made by one really dedicated person, and it made a really good package. So it's even code that I wrote for some initial KNet code that I worked 3 years ago, or 3 years ago, still runs. So it takes a lot of, the KNet developers take a lot of care to not break your code, and it's really stable. But yeah. Okay. So so now the web page where you want to go to is this one here. So it's, I use a URL shortener. It's tinyurl.com/JuliaEO21, and we are hands-on session 21 -code. So this is the web page where I all want you to go. And this contains all more information about this. Okay. So tinyurl.com/JuliaEO21-code. And I really don't want to lose any of you. So if you want to follow, please let me know if something is unclear. So I don't want to lose anybody. So if something is not clear, please raise your hand immediately, because I think it's
just so you gives you a warning.
I think you mistyped it. So let's check. It's maybe yeah.
I was just saying I got a warning. I think it's safe to click and proceed, right?
No. You I think you
mistake. Okay, mistake.
Yeah, try. Maybe you put URLs, tiny URLs or something like this. So just who of you was able to get to the GitHub page? Okay, great. And some of you have maybe some issues. Okay. Does it work for you now? There is no malicious software. Okay, great. Thank you. So this is, so everything you need to know is here or linked from here, okay? So yeah, we can skip it directly to the workshop material. So if you have it, you should already have it on your USB stick, right? So the USB stick that I passed around should contain everything you need to run the notebooks. So some of you forgot to copy it, or did not get the USB stick for some reason. Okay, so everybody has the data. Oh, and the USB stick is there. Thank you so much. Okay. So the next thing, is to remember where you put the stuff. Okay, so try to navigate to your file manager and find the Julia Earth Observation Workshop folder. Either it might be with Docker or without Docker. So I gave you two options. You can use this with Docker or without Docker. Yeah, but yeah, you should find like files 01 DYND data preparation, for instance. Okay. So everybody found this file? If not, raise your hands.
Both the Julia file and the Python notebooks are the same way.
Yeah.
Can I use the same Docker image as before, or do I need yours specifically?
Please, it's better to use my Docker image because everything is already pre-installed.
Okay.
If you use another Docker image, then everything it should theoretically work, but a lot of things need to be installed, and then you might be better off to just use Julia without Docker if you need to install the package anyway. So, okay. Okay. Okay, so I think those who want to use Docker, I would assume that you have already Docker installed, right? And so the next thing is to open a terminal, okay? And so in Windows, actually, there are two kinds of terminals, the old one and the new one. You should use the new one, which is called PowerShell terminal, okay? So you open a PowerShell terminal. Yeah. And the first command that you need to execute, if you use Docker, is this one. So if you on Mac, it's just a regular terminal. On Linux, it's a regular terminal. And so this command imports the image. Okay. Yeah. Sorry. Oh, sorry. Okay. And this will probably take a while. And so if anybody wants to do it later on, or you can, another option is to download it on the fly. Okay, but we don't do it here because we do not want to overload the internet. Okay. So this will take a while, I guess, to import it. So just in case you already it already worked, you can actually follow the README. I will, if you want to go ahead, you can already do it, but I will wait a bit to be sure that everybody got the Docker image loaded. Okay. So if you're not using Docker, actually, you can already do what's written here, installation directly with Julia Package Manager. Okay. That's the alternative that you're not forced to use Docker. You can also use it directly with Julia's Package Manager. Okay. But if you're using Linux, you have to be aware that it's one package that you need to be installed in addition. Okay. The matplotlib package from Python. Okay.
Is anyone else running compatibility problems?
Let me see. What kind of problems?
Yeah.
So you. So yeah, apparently KNX doesn't work in one, so it could not install.
Yeah.
So how many M1 users do you have? Do we have other on Mac M1? Sorry about that. Maybe with Rosetta, you can, but then you would need to reinstall. Yeah. Okay. So just to know, who of you already managed to do this, to Docker load JuliaEO? Okay. And who, so I know one case, but who is struggling? Who has some problems? Okay, so we can continue. Okay. And okay, so you already probably are in the folder containing the Docker image, yeah, right? Because you just loaded the file JuliaEO. Okay, so the next step is to execute the Docker image. Okay, that's the same as before. We type docker run and specify the port, the web port that you want to publish. By default is 8888. And the V is for volume. So our current working directory, pvd, print working directory, it's available inside the Docker image under the path home, Jove, and data. And that's the Docker image that we are running. Okay. And when this works well, it will print on a terminal a bunch of lines. Okay. So it will start environment, print a lot of line, and what you have to look after is a line like this. Okay. It say to access the server, open, don't do this, don't do this, neither this, it doesn't work for me either. Only the last option actually works and allows you to open a web browser with Docker inside, with all the software inside. Okay. And then you will get the standard Jupyter Lab interface. So you should get something like this. So a little bit show of hands, who managed to have a screen like this? Very good. Who is still waiting something to happen?
My physics just got to load them, so now I do the Docker run.
Yes, exactly. So the first step was to load it. So the easiest thing is really to copy and paste the command because it's really long. It's easy to get it wrong. Anybody else still waiting to get this screen? Anybody else? Okay. Do you need some help or just wait? Who of you is using the option without Docker? Just to know. Everybody's using Docker, or somebody you using without Docker, and still it works so far? Yeah, perfect. You can open the first file. You can execute this cell, so it takes a bit of time to load.
Yeah, one thing that might happen, it happened to me. I had another one open, which takes the same port number. So if that's the case, you can turn off the previous one, stop it. You don't need to delete it. You just need to stop it, and then you can solve it.
Yeah, that's a good remark. I have this all the time, and or what I do sometimes is to use a different port, but it's the cleaner is to shut it down, so you have to free our resources. But if something else important is running on port 8888, you just use a different port, and that works as well. So the typical error message that you will see is this: if address already in use. So if you see this, raise your hand if you don't know why you get this. Okay. So a little show of hands, who is able to, so within this interface, yeah, we can click on data and open the first notebook, okay? So it is called 01 Diva and D Data Preparation IPyNB. So we open the notebook, right? And you should have something similar to this. Okay. Is this okay? Still open? Maybe it's worth to use some code. Do you think I learned that memory, or maybe it's sufficient with some other work that you're doing?
It's not a PowerShell, it's a common prompt. It's got no PowerShell. It's already, no, not yet. I was just.
Yeah, you have to do it manually. So. Okay, look at the see if you get. So.
Okay. But because
No, it's different.
Yeah. Yeah.
It's different, yeah.
Yeah. So,
So just end this. Stop.
no. Here's the one. Local one. Yeah.
Just mountain in different direction.
Okay, so now I know I will start.
So let's see.
Yeah, I will try.
So The idea of this notebook is that you download some data for the Azores region and then make a first DIVA analysis, okay? So in the very first cell, we are loading all the packages. And if you're using Docker, it should already, everything should be already pre-installed. Yeah, for sure, thank you. What about that? Is this good? Also for the back? So, so we're loading DIVA, we're loading some other packages that we need to have, but everything should be already pre-installed in your in the Docker images. Or if you're using a Julia package manager, when you instantiate, that's a really important step. Everything will be installed as well. And so at first we're defining the bounding box, so the longitude and latitude range. Okay. So for the Azores region, this is about the longitude latitude range. So degree west would be the negative values. Okay. And for this simple case, we are just getting the data for 5 years, starting in 1st December 2010. Okay. So date time is a function from the dates module, which creates a datetime object which represent a moment in time. Okay. And actually, in one of our packages, we wrote a tool which allows you to download the data from the World Ocean Database. So the World Ocean Database is a quite well-known data source in the oceanographic community, where you can download the data via a web page. Okay. So what the FIS Ocean package does is actually to automate this process. So you don't have to go to this web page. So it simulates a user going to this web page and fetch for the data. So, but it asks you to provide your email address. So therefore, also in my script here, you have to provide your email address. But since this is a quite long process, so it takes about some hours to get the data. So typically we tell you per email once the data is there. So I automated, I give you already the subset that we are looking at. But typically what you would need to do if you work for a different domain, you would rerun this kind of cell. So it would then download the data from the World Ocean Database. Just curious, who of you already worked with the World Ocean Database, or is familiar with or heard about the World Ocean Database? Okay, so ocean people. Okay, so it is yeah, it is quite well for in the oceanographic community is quite well established. Okay, and but what we will do is just execute this cell. Yeah, it will just download the file, all the data. Okay. So if you do this, it will just print a message, data file already downloaded. Okay. I'm just wondering, everybody got this message, data file already downloaded, or somebody else got, I'm now loading the data? Just because the data file should be in the same directory. Okay. That's the notebook. And if the data is somewhere else, it will not find the data and will download it. So if you are at home with a fast connection, that is not a problem. But here, yeah, the idea is that you have already the data via USB stick. Okay. So maybe show of hands who is already at this step. That's the data file was located, okay. And who is maybe has some issues. Okay. So the next thing is then to load the data in memory. Okay, actually it's not that large. It loads it quite fast, and then to have a look at the data. I always like to look to the data together with the bathymetry, at least for the coastline. Therefore, I also load the GAPCO, a part of the GAPCO bathymetry. So the bathymetry should be there as well. And then we make a first plot of the data. Okay. So what we do here, actually, we're looking just at the data which is near the surface, less than 5 meters. So ops depth is the depth of the observations. And so for now, we're looking any months, the months 1 to 12, but you could easily narrow it down and to just have, say, January, the data distribution January, yeah, it's much less, okay. And so you can easily narrow the distribution. And so this is the Azores region. You recognize here the Azores Island. Okay. So for the plots, I still mostly use PyPlot. And here, that's a handy way in PyPlot to get the aspect ratio more or less correct. Okay, you don't want to have plots where you don't want to have the landmass stretched out in an unrealistic way in X and Y direction. So you essentially look here. By is the latitude. So you're taking the mean of the latitude and then set it to the inverse of the cosinus of the latitude, so that the data looks more or less correct. The aspect ratio looks more or less correct. So it's a very easy way to make a map projection. Okay. And the next step is to look, for instance, to the distribution over time. Okay. So in situ data is not only very inhomogeneous distributed in space, but also very inhomogeneous distributed in time. Because a lot of the Argo network that already Gael mentioned was really quite kind of revolution for ocean data, because the amount of data that we have really increased tremendously thanks to the Argo data. But here we are in the phase after the Argo data. I think it was 2008 where we have Argo was launched, but still we see here the number of data still increased quite a lot. But if you would extend it before 2008, it would be really, really even more. Okay. So typically, when you do a climatology, you have to take things like this into account. You have to take into account the change of data distribution over time, but also the change of if there are any significant changes in the system that you're looking at. Okay. This is the first notebook about the data preparation. So we have downloaded the data and made some really first checking the data, the horizontal distribution and the temporal distribution. Okay. So I'm just wondering. So did anybody had some issue about this? So, or it worked for? So maybe just raise your hands if we're not able to do the last plot. So I don't want to lose anybody, as I said. So maybe just tell me if there's something working with this. Okay. Just go. Okay, you have to distance it. Can you open this? Yeah. This was for the package. If you use a package manager, this was an initial step. Yeah. So since all the packages are not installed by default, you have to instantiate. Okay. And also the use. Yeah. Yeah. Normally. Yes. No, that's not necessary. So that's you can really delete this because the list is already integrated. So this you don't need. It takes some time to instance. What you have to do is only this. So this instance. So along with notebook, there's a list of all packages that's installed. That's a package toml, managers, toml files, the 2 files, tells you what's needed in instance. You just install everything. What about you? It's from the ocean. Yeah. That's the PVD was initial. Okay, so So now the next thing is actually to, once we have prepared the data, let's head over to the next notebook. Okay, so we have open notebook 1. And now let's open the notebook 2. So the 02 D/D examples analyze D/D example analyzes Azores. Yeah. I will do it from here. I have this. Probably shouldn't. So you should have the second notebook, which should look like more or less like this, and where we actually will do our first DIVA analysis. Okay. So as usual, it's quite important to execute really all the cells. Yeah? And if there is any error, just raise your hand and we will look at it together. Yeah. So very important. Let's open the. Let's import the packages. File is already there because we already. Bathymetry is there as well. Now again, reload all the data into memory. And then the first thing to do is actually make just a basic range check of the data. So let's just have a look. What is a typical range of longitude, latitude, depth, and time? And just to see if we don't have any obviously bad data in the data set. So next thing is to then to define the resolution in longitude, latitude. So here we make a very small test, which just use a tenth of the degree of resolution, which is actually quite good. But take in mind when you increase the resolution, yeah. So essentially, if you increase the resolution by a factor of 2, your grid cell will be increased by a factor of 4. Yeah? But when you need to solve the linear system on which DYND is based, your memory consumption will increase by a factor of 16, something like this. So 4 by 4, 4 to the second power. So the memory consumption can grow quite quickly if you increase the resolution. Take this in mind, please. Okay. So that's for the horizontal grid, and that's for the depth levels. So for simplicity, we're just considering 3 depth levels, so it runs faster. And then the most important parameter for DY actually is this epsilon 2 parameters, which tells us how large the error of the observations are relative to the error of the first guess. So, so this is an A-dimensional number. Yeah, so it's a ratio of 2 different errors. So the first guess in DY would be just the average. Yeah, and this epsilon 2 tells us how much more accurate observations are than the special average. So 0.2, it means the observations are 5 times more accurate than just a spatial average, for instance. Okay.
That's good.
Yeah.
Yeah, this is great. Was just wondering whether you also had maybe an option to provide weights separately for the two in kind of.
Yeah, excellent question. Excellent question. So a separate weight for different observation, you mean?
For the first guess, say a map, and then for the in situ data, something that might be spatially variable also. That's kind of what I was wondering.
So a different way to specify the error of the first guess and the error of the observation?
Yeah.
Actually, this is just a ratio of the two.
Mm-hmm.
So the DIVA does not need to know the error of the first guess in absolute terms, and does not need to know the error of the observation in absolute terms. It only needs to know the ratio of both.
Okay.
Okay. So so if you write a cost function, you have 2 terms. It has to be close to the first guess. It has to be close to the observation. If you multiply every of these 2 terms by 5, the cost function will still be the minimum of the cost function will still be the same. So therefore, we only need to have the ratio of these 2 terms.
I understand. I guess in my mind, there's a slightly more general problem where these errors are heterogeneous spatially. For example, because of geophysical noise.
Yeah, okay.
And so you want to do something a little bit more detailed, but
yeah,
maybe that can be added later.
Okay. So what you can easily do is the spatial variant error of the observations. That's easy, but it's hard, and well, it's not possible currently, and it's hard to do a spatial variant of the background. That's so far. Okay. Okay, excellent questions, thanks. So the next thing is then to define the correlation length. Okay, and so the correlation length is here defined in meters. And we do everything in meters in Julia and in JuliaEO. So this is actually the same as written like this, but it's easier to read. There's actually 300,000 kilometers. So if you would reduce this parameter, this correlation length, you would actually have more details, but you have also more noise. So it is a kind of a trade-off to make. And so for us, we could also fix a vertical correlation length because we're just looking at 3 layers. But if you're looking at the complete ocean, down to its bottom, it's typically you would have a smaller correlation length near the surface, smaller vertical correlation length near the surface, and then higher vertical correlations near the bottom. Okay? That's why it is a bit more complicated here. But don't worry about this too much. Okay? But these are really the 2 important parameters: the correlation length and the epsilon 2 parameter. Do you have any questions about this, or some doubts or some error messages or something which everybody managed to go that far? So the next thing is actually to define the time axis. So when you're working with climatologies, there are really different ways to approach a problem. So sometimes you want to have a monthly climatology, the average state of January, the average state of February, and so on. Sometimes you only want to look at seasons, the average winter state, or sometimes you want to have just the average year state, but then for every year a different state. And so this is in order to capture this kind of flexibility, we use a variable that we call time selector. Okay, but here we use the time selector year list, month list, which means that we are making a seasonal climatology. So we're taking all the data from 2010 up to 2015, but we're doing a climatology for every season. Yeah.
Just a question regarding what are the current methods used for the World Ocean Atlas climatology?
And very good question.
It's not Viva, right?
It's not Viva. No, it's Viva. Very good question. So the World Ocean Atlas is based on the World Ocean Database, but the World Ocean Atlas is provided gridded climatology. And what they're using, the method is called successive correction. It's essentially when you have an observation, you spread it around iteratively. Okay. So it's a kind of a simplified form of optimal interpolation. And the advantage is really efficient. Yeah. And you essentially only need to hold your result in memory and the data in memory. So it's not, you don't need to, there's no linear system, complex linear system that you need to solve. But it suffers from one of these errors that I mentioned before. So the leaking through the so with this method, it's difficult to implement this kind of barrier effects. Okay. But the method is called it's called the Barth scheme. Sometimes people claim it's optimal interpolation, but it's actually, when you look to the paper, it's called the Barth scheme.
Maybe it's when you have more data, it's better, right? When you don't have so much data, it's less.
Actually, I would argue the other way around. If you have a lot of data, it really doesn't matter what you do, because you have a lot of data, you will have an accurate result anyway. But if you have not a lot of data, then it's maybe better to investigate. Okay, what would be the optimal choice of technique? Because if you have a lot of data, probably all of the methods will be really similar anyway.
Thank you.
You're welcome. Okay. So, but don't forget really to execute all cells, because it will define variables that will leak later on. And here, one of the steps that we have here is to define all the metadata that will be in the netcdf file, because d will directly, the output will directly be a netcdf file, and you want to have this netcdf file complete concerning the metadata. And there is some, here this metadata object is an ordered dictionary where you put all this data, additional metadata. But don't worry too much about this data. It's but for other projects or European projects, we have standardized on what kind of metadata you put into it. And the next cell actually takes this metadata and enrich this metadata by contacting a web service in the UK, which adds some more information about the different variables. So there's the BODC in the UK, which has a repository of all names, of all parameter names, with in which parameter code to use, and that's the next step. So if you don't have internet connection, unfortunately, this step will fail. But I think it's just a small download. I think it will work for us. Okay. And since running Diva can take sometimes a long time, we want to plot the result as they are generated. So this is the function plot res. So it plots the result. So we're defining this function, and then it will plot for us on one side the original data, on the other side the interpolated feed. Okay. This line gives an error? This one? The next one? I didn't check your internet connection.
No, it's not, because the server are responding that they are all in the same origin, so they will not respond. Because we are always making a request from the same position, so they will not respond because it's
You say that
it's because we are always here, or we are always
Can you try this again? Because every time we execute no, it will change. Can you show me the
like I work all on the notebook.
Maybe we did it all at the same time. Yeah, no, it's very interesting. So who also has this problem with the knowledge because I changed the that's clever. But no, it didn't. But then yeah, I did. Okay, let's stop it. I think you should interrupt if you don't you mind to okay, this is the Wi-Fi. Yeah, this you don't no have internet. Yeah. Oh, whatever works for you. Floats my what he said, many people from the same place, right? Yeah. But if you change the IP address, if you change the Wi-Fi, you change the IP address. So it should not be able to see that we are the same people. No, maybe I don't. It's another. Can you copy the message? Oh. Because we stopped. No, I just I should have no message. It's the same. But the forbidden one is one, yes. Oh yeah. Try to change it. Yeah. But can you copy the message before? So yeah, just send it me by email. Can you just save it and then just save it in the text file and send me later by email? Unexpected. Yeah, that's weird. It's really a very small file. But it's really just an explanation.
When you get there.
Can you try again? Yes. So,
Yeah, change
It's also
I will show you what you can. Let's try something. Who else has also this forbidden error when you want to connect to this by executing set? Not responding. Okay. So then you can interrupt the kernel. You can choose cell. Yeah, you can interrupt the kernel. Make sure that this circle is white. It means Julia's node not running anymore. Okay. So if it's running, it will be black, but make sure that's not running anymore. And if it does, if just interrupt doesn't work, you can also say shut down. Okay, that's forcibly will kill Julia and then rerun the previous cell. So what we'll try, I hope it's, I did not test it, but we just set, for those who have a problem, to the metadata to empty. Okay, the empty dictionary. Let's see if it works. I don't know. Okay. And then if you do this, you can hit cell run all. Okay. And then we are making the debug analysis. Okay. This is the idea, is if you have an error by getting the metadata, you should set the yeah, you can try to set the attributes to empty dictionary. Okay. Let me see if this works. So I set it to empty. I redefine the plot res function, and then I start. Oh, okay. No, I have different notebooks open. Okay. So everybody who has this problem got the time to copy this line. NC global attribute equal NC var attribute equal dictionary empty. Yeah. So only if you have an error at this stage. Okay. Okay. And so the next step is then to actually launch, to run Diva. Yeah. And we'll print out a lot of messages, but more important, in the end, it will also show the analysis and the observations together. Okay. So, but we are just plotting for the surface. So you will see the result and the surface and the analysis. Okay. So maybe are you?
It works, but I don't know why.
What works when you said
Why it works without dictionary?
it works with empty dictionary? Yeah, it just tells you I don't care about metadata. I put the metadata to.
Yes, why
no, the netcdf will have the data in the netcdf file, but you don't have the metadata, the author, and things like this. And, it's the metadata, yeah, it's just things. Who you are, in which frame of the project this is, and what kind of variable it actually. Okay. Any any show of hands whether was not able to see this kind of plots? Okay. What about you? Did you manage to? Okay, this is okay. Don't have to change it. Okay, so one thing that you can see, if you have any suspicious data, any bad data, it will strongly impact your analysis. So for instance, here, there are some data points which is a really low temperature. Actually, the color bar is limited, you don't see it, but this point has really low temperature. And as a result, in the analysis, you will see this kind of really strong anomaly. And yeah, and it's quite likely that this is actually a bad data point. Yeah? So we don't want to have this in our average. And so even though that here I only loaded the data which were qualified as good in the database, it's unfortunately still often the case that that there are bad data which are undetected in the database. Okay. So in the next step, we actually look okay, no. Okay, okay. Yeah, this is a step you cannot execute twice, unfortunately. Okay. So the next step is actually to save the residuals. I'll save the observations, and we look especially to the residuals. Yeah. So the residual for us, it means the difference between the actually observed value and the analyzed value. Okay. And so there's a function extrema which looks at the minimum maximum. If you just directly look at the residuals, it will tell you none because there are some nuns in the residual. Okay. And typically you would exclude the nuns, and then you get, okay, the residuals is between almost -20 to +10 degrees. So that's really, really large. So so by looking at the residuals, it would be a way to exclude the bad data. Yeah? And we can then also because along with every data, we have also an identifier. So you can look, okay, for which observations do we really reach the residual of minus 19 degrees? Okay, so that's here. We can then check back. Okay, this world ocean data profile probably has some suspicious data. So that's also good feedback to give. What are the data which probably should be excluded? Okay. So in the next step, we save the residual. And here we can also plot the residual spatially. Okay. So here we're just looking at the January and near the surface. And we're limiting the color bar to -3 and +3. So if I would remove this, I don't know why. Okay. Okay. But in Diva, there's also an option to give you the coherence of every observations with other observations around. Okay? That's what we call QC value. That's a value which helps you to do quality control. Okay, so every time when this QC value is really large, yeah, then you probably have a suspicious data point. Okay, so and when you run this, you see, okay, the QC value is almost close to 0, except for some of these values where the value is quite large, and this means that yeah, these are data which are incoherent with other data points. Okay. And the next thing is then to decide, okay, I want to discard all the data points which have a QC value larger than 7. Okay, so I say my good data points are those where the QC value is smaller than 7. Okay, you can look at the histogram and see, okay, by doing this at 7, only very few points, you will discard only very few points. And then it will make your analysis much more realistic. Okay. So what we then do for the final analysis, we take all the data points and just exclude the bad ones and keep the good ones. Okay. This is in our last step, and then we will do the final analysis when we have just a good data points. Okay. Okay. And you should see a much regular field if you do that, because you remove the bad data. Okay. So I was wondering, those who have the problems with the metadata, does it solve for all of you by setting it to an empty dictionary? Were you able to continue? No? Okay, I will show it again on this slide. This is the line that you have to add if you cannot retrieve the metadata. But for those who don't have an error, you don't need to do it. So Julia, will start? Yes. So, no, it's just. Okay. You run. Okay. She does. This one. Yes. Okay. Yes. Okay. Yeah. Okay. Okay. So now run. No, it's a bit different for me. I have an option to say run all. Let's say that's then it's run. Yeah. And then we should to do the rest of the notebook which not have any problems. Yes. Okay. So you can keep this notebook running if it's still doing something. Let's open the last notebook, which is the third one. So I open it from the terminal, but you should be able to open it more conveniently using the file manager. Okay. So this notebook does implements the Dinkai technique. Yeah. So that's a neural network to reconstruct missing satellite data. Okay. And so typically these notebooks would require a GPU, NVIDIA GPU to run on. And so yeah, I don't have a GPU on my laptop. I don't know if you, but I won't be surprised that most of you have a GPU on your laptop. So for this reason, I only explain the data preparation, and then we just download the result and then have a look at the result. Okay, we'll just skip the part where we actually run the neural network. And anyway, it takes a long time. It takes a long time to run. It takes maybe a couple of hours to run. So we won't have time anyway to do it. Okay. And but everything you need to do if you would try it on your own data is actually explained here. Okay. So as before, we're defining a geospatial bounding box for the data that we're interested in. Here again, we're looking to the Azores region. But later on, if you would try to use a different domain, that's what you would need to change, the longitude range and the latitude range. Okay. And we're also loading the data, the start and end time, the time range that we're looking at. So typically here we're looking 3 years worth of data starting at 2017. Okay, and we're using here the MODIS satellite data. MODIS is for temperature. Okay, so typically you would like to have time series as long as possible when you're working with neural networks. And the MODIS is a relatively long time series. That's good. Okay. So here we're defining some file names, like the name of the file is called MODIS subset. and we are working in the current directory. So if dots means the current directory, but typically I do my notebooks in one part of the computer and my data files in another part of the computer. So if you use the same approach, your out here would be the part where you put the large data files. Okay. And here we just download a modis subset if it's not already there. Okay, but you have it already, so this cell won't do anything. But if you are interested in a lot of data is actually structured along a lot of satellite data. They are distributed for one file for every day. Yeah? So if you want to have 3 years of data, you don't want to load all the data by hand. Okay, that would be quite a nightmare to do. And so typically you would use Julia or typically Julia to download all the data. And the URLs of these data files actually you can easily they follow the same pattern. Yeah, so they have the date in it, the day of year in it, and things like this. So in Julia you can construct the URL for a given day, and then you just download the data. Okay. And every data file actually contains the whole world. Yeah? But we are just interested in the Azores region, so we need to subsample the netcdf file to our region of interest. Okay. And there are different ways to do it, and one recent way that I added in NC datasets is actually to take the netcdf file, or for us it is an opened up URL, and then saying, okay, I only want to have the latitude. I only want to have the latitude within this range, and the longitude within the range that I defined before, yeah, within the bounding box. Okay. This allows you to subset the netcdf file and then write it to the disk. Okay. But for us, the data is already prepared. No? Okay, so we're just loading it here. Okay, so everybody should be able to execute this line. It should not really add a lot of. It should not be download anything. So let's have a look. SST is now an array with about 200 times 160 elements, and we have about 1,000 data points. Okay. If you want to plot, let's have a look at the. Okay. So that would be the first time instance. Okay. What I did here, so SST is a 3-dimensional array. I just extract the first time instance. Okay. And in this array, we have actual values, yeah, and we have missing values. Okay. And in Julia, the missing values is a special type, which is called missing. So for instance, the first element. Oh, that's actually value, but let's try another one. It's missing. Okay, so that's the way that we are working to declare missing values. So one of the common questions why we don't work with nonce, okay, for missing values. So most of MATLAB uses nonce, X-array in Python uses nonce a lot, but the idea here is nonce only work with floating point numbers. Okay, you can have also integer numbers and missing values in those. So you don't want to convert integer values to floating point numbers because you can lose precision with this. Okay. So that's why Julia works with, Julia gives you the possibility to have an array where the different elements can either be floating point numbers or missing values. So L type just tells you the element type of different numbers. Okay, but unfortunately, the PyPlots package doesn't work quite well with missing values. Just the plots package handles them correctly, but in PyPlot, I have to replace them by none. And that's what the no missing function does. Okay. And the convention is a bit weird in the sense that the first dimension is actually the y-axis and the second dimension is the x-axis per default. Okay. So PyPlots adopted the same convention than MATLAB before, where the first dimension is the y-axis and second dimension is the x-axis. So we have to transpose everything to have it something more, to have the axis in the same direction, in a good direction. Okay. Just want everybody got to manage the plots or to got it at this point. Okay, so now the next thing is to just, as before, to range check the data. We want to have the minimum and maximum values, or there's two extrema of the variable SST and qual, which is the quality flag, but we want to skip the missing values. That's the skip missing function. Okay. So here actually we can keep no additional quality flags, quality control is necessary, but in other tests, I need actually to discard some data larger than 40 degrees or with a quality indicator larger than 3. I had to mark them as missing, but actually in this case, none of them is marked as missing in addition. Okay. So once we have cleaned up our data, we'd save it again to a netcdf file. And now we need to decide, in this image, where we have land and where we have ocean. Okay. And the only thing that you have is this image with I have data and I don't have data. Okay. Obviously, when there is land, you will never have data, because you will never have a surface temperature measurement when there is land. So therefore, we're just looking at where we typically have never data, and then we mark it as land. Okay. But also, it can be problematic just a grid cell where you have just one-time data, and just some small bay which got flooded just one time, but otherwise it's only masked land. So typically what we do is say, okay, if for a grid cell to be considered C, it has to be at least 5% of the time covered by the ocean. Okay. And this adds to the netcdf file a new variable, which is the mask. Okay. Another important thing is we have to remove some data from the data set. Okay? We have to mark some points as missing. Okay, and that's using the step add CV point, which adds cross-validation points to the data. Okay, and here in our case we are adding 10% or removing 10% of data. So we adding some kind of synthetic clouds to the data sets. Okay. So some of you maybe have an idea. How would you remove some data from the data set? Do you have some ideas? How would you, what would be the approach to remove data from the data set? Random? Yeah, exactly. We did also random before. That was the most obvious thing to do. We just said, okay, a random 10%. And this gave us an error which is really, really too good. It was too good, the error. You have an idea why? So if you just choose randomly 10%, just really random, take the rand function and just exclude 10% of the data. They will not be together. Exactly, exactly. So if you do it really randomly, you have isolated pixels that were removed. Okay? And we did actually this, and that's saying, okay, the error is really, really low, but if you just exclude pixels, yeah, it's really easy to reconstruct them because we have all the neighbors, right? Okay. And so, but what you typically have is actually you have clouds which have a special extent, right? And if your cloud is 100 or tens or 100 kilometers in diameter, so it's a large area that's actually not measured. And then it gets the problem to reconstruct this data is actually really hard. It gets much harder. Okay? So the idea is that when you remove some data, yeah, using cross-validation, you should not make the problem too easy. You should actually remove. What you add to. You should add something which really resembles the cloud. Okay. So the approach that we did here, we took the yeah. Do you have a question?
I was just going to say that either Julia has a neutral landscape package which does sample quality with just structured randomness and plot randomization and like that. So you can choose the kind of company that best matches this situation, and then you could just explore like kind of cut off that.
And what is the approach to use the random data?
There's like 10 different ones. It's like just lump them spatially instead of having.
Yeah, that's a very, very common form. So, and so the approach that is using here is let's take the clearest image in our data set, yeah, and then choose randomly different data, yeah, and just copy the cloud mask from this different data to the very clear image, and then repeat it for the second clearest image. Yeah, I have a clear image, maybe with no cloud or very few clouds, and then get the cloud mask from another image, yeah, and then exclude all the data there. Okay, so it is kind of iterative processes where you intentionally degrade your clearest images, yeah, and then add some clouds there. Okay? And we're starting with the clearest images because if you would take an image where you have very few data, you don't want to exclude. You don't want to cover everything. That would be, but you want to. Yeah, that's the reason why we take the clearest images. Okay. And that's what the add CV point does. Okay. And so in the end, we exclude about 10% of validated. So it stops when it reaches your target number of validation data. Okay. So the next thing is then to run our neural network. But this we won't do it here because it will take a really long time. Okay. So it checks if CUDA is functional. So we're using here neural networks which support CUDA. So this is only the NVIDIA, only on relatively recent, but no, only the NVIDIA GPUs support the CUDA API. But there is also some work to implement AMD GPUs. but that's not as mature. Okay. So if CUDA is not available, it uses CPU, but this will be really slow, and we don't do it here. But the notebooks should still run on the CPU, but it's it will really run for a long time, and it will not be fun to watch doing it. Okay. So in the next thing, I define some hyperparameters. So the number of epochs to be run. And so the epoch is actually means how many, so the neural network is trained iteratively. So the data is split into batches of 32 images. Yeah. And it computes the grading of the cost function using these batches and updates the weight of the neural network. And then it goes to the next batch and so on until it completes, until it went through the whole data set. And this is one epoch. But it repeats it several times, and here we're using 1,000 epochs. And another thing that we do, which is slightly special, we actually saving the result at different epochs and then taking the average of it. Okay. So here, this is how you would run the neural network, but we don't do it here. Instead, we're loading the file which are already prepared for you. And this is the loss function. So initially the neural network is really bad because you initialize it randomly, but as you optimize it, the error will go down. You probably can go even further than 1,000 epochs to drive the error even smaller. Okay. So the loss here represents the negative log likelihood. That's a technical term. So it's the logarithm of the probability. Yeah? Of the probability that you're having your observations, assuming that the neural network will give the right answer, and you want to optimize this negative log likelihood. Okay.
That's good.
Yeah.
Can I ask you a quick question on the...
Sure.
Thank you. Yeah, I was wondering, because it's based on features that are identified in the images or the data, kind of how much does it generalizes to different regions, depending on whether you take absolute values of SST, for example, versus anomalies, if it's a concern or not with the autoencoder? Like, you know what I mean? If you train in the North Pacific,
yeah,
can I apply it in the Southern Ocean?
Yeah. So in this case, it would not generalize at all because I use longitude and latitude as an input. Okay, so I give the neural network, okay, this is the value and these are the coordinates. And if I would use a completely different domain, it will have coordinates it never saw before. So it will be terrible to generalize. Okay? So if this is your objective, you should not include longitude and latitude in the training data set, or you would say, I will need to train it somewhere a bit everywhere in the world. Yeah? So what we did so far, we concentrate on the North Sea, we concentrate on the Mediterranean Sea, and we use only data of the Mediterranean Sea. But we did not yet check if we can, in fact, do a neural network which can be valid everywhere. But that would be nice to see. Yeah. Okay. So this is the cost function, yeah. And it is, you see a bit of noise in there in the cost function. Do you have some ideas why we have noise? Why it's not just a line going smoothly down? Yeah, exactly. We're not computing the gradient on the full data set. You're only computing the gradient on the subset. Yeah? And the subset is even choosing randomly every time. So that's why the gradient will be every time a bit different, and the loss function will also fluctuate a bit. And actually, this actually is a good thing, because when you optimize a neural network, you can escape a local minima by using this mini batch gradient descent. And that's also one of the reasons why it's also sometimes called stochastic gradient descent, because you're randomly choosing a mini batch every time. Okay, so I think I'm almost out of time. So in the last step, we're just plotting the all the results. So if you execute this function, it will plot all the results, but only the results where we had some cross-validation. So I guess I will just open this in a file browser. So these are the results of the neural network. Yeah, so typically, so in panel A, you see again the original data, and B, where we added some clouds. And here we excluded 13,000 pixels in this image. And the neural network only sees what is in panel B, and then tries to make a reconstruction. And something quite interesting when you work with this high resolution data set, you get the impact of cloud shadows in your reconstruction. And are sometimes data which is really cold. So I'm really not sure if in the original MODIS data, for instance, all these cold temperatures near the cloud edges are actually really realistic values, or if these are just mislabeled cloud. Okay. But I think I will stop here and give Gael the opportunity if you want to or yeah. Okay.
Either way, if you want to go in the next notebook, you can.
No, that's all. That's all. So the first notebook will be for tomorrow.
Okay.
No, thank you.
Okay. All right, so I just wanted to show a couple notebooks that you will find in the here in the Julia Climate Notebooks webpage that have to do with in-situation data sets and how to access them. So I ran them separately on my laptop because I was already using the Docker image from Alex. So this should work either way, and they should be fairly fast. You'll find them on the Julia Climate, so github.com/JuliaClimate, and then the notebooks. Very briefly wanted to highlight that we have now a few different things. So the World Ocean database is a great one too, in fact. Ways to interrogate some of the ocean databases out there. So here is one that I got a bit familiar with recently, which is the Oceanops platform. If you're an oceanographer, you're probably seen these type of things before. This used to be called GCOMOps. It's now called Oceanops. And this is a group that is collecting all of the metadata from operations at sea, which includes floats, drifters, and so on, as well as in-situ cruises, so ship cruises that are planned or in the past. So it's a good way to kind of figure out what's out there, essentially. right? And they should have just about everything you're interested in. So here, I'm showing Argo. The operational ones are blue points. The planned deployments are in red. The drifter dataset from the global drifter program are in green. And I have the tropical moored buoy. And you can just change that to a bunch of other things. Here I'm looking for vessels of opportunity data sets and so on and so forth. So it's a nice way to kind of figure out, I don't know if you're interested in anything. I'm going to do, hey, glider, let's see. Yeah, we don't see much. There's a little bit there. So it's a good way to sort of explore sort of through everything else that I'm going to show. And this is just for the metadata though. So you then want to go to something else to get the data itself. Here is a few, in addition to Argo and the Global Drifter program that I have already gone through. So the NOAA buoys, they have a nice little API that you can interrogate. And so you can, with this notebook, explore, pick whichever one you want. These are kind of nice because some of them are very long time series. We've used them in classroom for like 12-year-olds to make like a little kind of climate change demo in math class. Along those lines, here is another one that's to the credit of our colleagues in Hawaii and Woods Hole. This is the so-called Woods mooring, which is a very rich data set, a time series that has a lot of different variables. So again, we have like now a little, oops, a little way to explore it remotely and then subset it. Couple more, well, just one more, the glider data sets, because I mentioned it before. So these are sort of slightly more rare data sets, but they're very nice because they have very high sampling rates. And so there is a bunch, just going to go change that. That didn't work for me. I guess I didn't download that. Yeah, there you go. So just, and same thing for Argo and the Drifter program. If those are things that you use. We have now simple little notebooks for you to get the data and look at it. And this is all within the oceanrobots.gl package. So that's all that I was going to mention, just a side complement to what you are describing. And if you have other ones that you are interested in building like this, please reach out. I'm hoping to get kind of a semi-comprehensive way to approach those heterogeneous data sets that have very kind of high scientific value. So that's it. Thank you all. And I'll leave it to that.
So we'll now have a coffee break until 4. We'll be back for the general hackathon. For those who are following us online, we end up the day here. Thank you very much for staying with us. And we'll see you tomorrow for the final day of this workshop. Thank you.